right, welcome everyone. Um, Before we begin, do let me know if the sound is okay. I've got a fan going with the AC as well, so I try to play around with the microphone settings to kind of drop out any of that background droning noise. But if it's weird or if it's too high, too amplified, not amplified enough, just let me know, and I can adjust it. So with that said, welcome. This is the summer office hours. Try to do these as often as possible. I've got a really nice set of questions this afternoon that I'll go into in as much detail as I can. As we're going through, if you have any questions, any follow-ups on any of the discussion, please feel free to drop questions in the chat. Thanks for the sound check, JD. Welcome. Yeah, feel free to drop questions in the chat. You can also drop them in the Patreon comments. Patreon page might not update, so I'll check it occasionally. And then if you're watching after the fact, and if you have questions, feel free to drop comments in the Patreon, and I will answer as much as I can. It should be, the settings should be that you can post any comments with a free Patreon account on this particular page. And if you run into any issues with that, just let me know. So let's just jump into it. The first question, a little bit less technical than some of the others, but it's one I'm getting a lot recently. We've talked about it on some, I think we talked about it in the last office hours as well. But kind of the general question of being interested in a more principled statistical approach, especially in these applied settings, and kind of being in this limbo of recognizing the limitations or frustrations of kind of current methodology and current teaching, and wanting to do better, but not necessarily knowing where one can learn about how to do better, as well as where one can go to have an opportunity to do better, to apply yourself using these tools in a productive way, while also maybe learning. And this is a really tricky question to answer because there really isn't any universal answer. And I don't mean that in a, well, there's lots of nice university programs and you can choose any of them. I mean that in kind of the truest sense of the word. There are opportunities in every field, every industry, every little corner of the world that you would never expect that end up being the most engaging, productive, and rewarding. And the challenge that these aren't indexed anywhere, these are not really known. A lot of times those opportunities, the people in them already aren't even aware they need this stuff. And so it's really challenging to find those connections. One thing to keep in mind is that I don't know, I guess this is changing a little bit, but for a long time, the statistics or data analysis groups at a lot of companies were kind of built up ramshackle, right? Everything was kind of made up on the spot. You typically have a company that would all of a sudden want to do something data related, so they would hire somebody they knew, a friend of a friend, a colleague of a colleague, a classmate, who not even necessarily was doing science or doing statistics, but maybe was this adjacent. A lot of physicists, astronomers, and the like would end up getting hired, and then they would establish the data analysis culture at that company. And that culture would determine who gets hired, what projects people work on, and the like. And then what would end up happening is that culture, that kind of idiosyncratic culture for that company, would you would have to be able to kind of decode that, understand how to apply for a job there. So you have all these like really talented people who have great resumes, they know their shit, but they aren't necessarily presenting it in a way that idiosyncratic company culture can appreciate. So when they apply, they just get rejected, or maybe they get an interview or it doesn't go anywhere. So there'd be these horrid stories from people who should not be on the market, but yet would continuously go out and have these horrible interviews and not get anywhere. And then at the same time, there are stories of people going into some companies where maybe there wasn't a data analysis community or culture that already established. So there was, and it happened to luckily be a good one. And so much of it was fit, cultural fit, more than it was anything else. And that's really tough to navigate because there's no way to know a priori. There's no way to search. There's no way to identify where you want to go. And so that's one thing to keep in mind. I don't think there's necessarily a resume that you have to get a good job. There's not certain programs academically. Getting a master's or a PhD isn't necessarily going to improve your chances. It might in some places, it might not in others. Having a certain skill set might help, might not. Again, it's kind of all over the place. And one of my favorite examples of this is, I think it was Stitch Fix. They had some kind of press release or article talking about their analysis group. There was a bunch of former astronomers, and they talked about, they were effectively just doing PCA, but they talked about it as if they were doing quantum mechanics, because that's where they learned. The astronomers learned about eigenvalues and eigendecompositions was, largely from their kind of intro quantum classes in school. And so when they see something like PCA, even though it's really just doing linear algebra, they think about it as quantum or application of quantum mechanics, and then they start talking about it that way. And if you don't know any better, it might sound super impressive, or it might sound really weird and like they're kind of missing a larger picture. In some sense, both of those things are true. But I think it just really demonstrates how challenging it is to effectively navigate those spaces. And so, the Discord, the probabilistic modeling Discord server, there is a opportunities section or a career. What did go look? What actually call it? Networking section. And so if you're on the Discord server and you're looking for a job, or you're looking to hire, and you're specifically interested in this kind of narratively generative probabilistic modeling stuff, either because you know it and you want to apply it, or you want to learn more about it, throw a message up there. I know some people have been hired. It hasn't always been a success on that forum, but it's another opportunity to put yourself out there. In terms of going how to improve your skill set, learn how to use these tools better. I don't think there's any real academic program that is stellar for that. You can get lucky and find an academic program where, and it can be anything from a science field, something like biostats, which is often kind of just like a pseudo applied stats with some weird baggage, at least in the States, to stats departments. You'll learn stuff from those programs. Whether you'll learn anything useful is an open question. Oftentimes, it's much more about, say the advisor you have and any particular projects you might work on. Or in a larger respect, it's the networking and the people you meet in your cohort and the people you meet at that school that might be able to key you in to opportunities going forwards. So, by no means should you discount those possibilities. If you find a program that looks interesting and you can reach out and talk to potential advisors and it sounds like there might be a match there, yeah, go for it, right? But you really want to go for it in the sense that even if you don't get a job out of it immediately, you enjoyed the process and it was rewarding and you gained something out of it. And then if you happen to get a job immediately after that, hey, that's a bonus, right? But I think both the kind of networking and finding opportunities and finding a job and learning, they're both kind of these slow, deliberate, organic processes. It's not anything that you can just hit a bullet list and go off of. Finding a reference or a resource on a topic that really speaks to you and where you're at and what you learn, what you need to learn next, that in itself can be a large struggle. And because nobody's really going to be at the same place as you, nobody will be able to recommend that resource to you. So similarly on the learning side of things, I think you just have to kind of be okay with taking things step by step. What is it that you want to learn a little bit more about? Can you find a good resource for that? And just try. And if it's too difficult or if it's relying on knowledge that you haven't acquired yet, then step back and try again. And it's going to be a lot of guessing. It's going to be a lot of trial and error. Not so much because a coherent path doesn't exist, but more that the path that's going to be coherent for you is not necessarily going to be a path that's coherent to anyone else. And so it may not be obvious for other people to be able to, what path they should be recommending you for. It's always something I'm a little bit hesitant about when people ask for recommendations or references or how to approach something. I don't know what's going to be good for you. Maybe with a lot of back and forth, I can get a sense for that. But it's a very time-consuming process to really kind of hone in on where somebody's at and what the next best step for them is going to be. It's going to be more code-heavy, more math-heavy, etc. That said, one thing I can recommend more abstractly is, you mentioned wanting, struggling with some of the deeper math and, with the linear algebra derivations of things. That's certainly something that you get better at practice. With practice. Although a lot of the reason why those derivations kind of are so obscure is not the right word, but opaque. Let's go with opaque. Is that they take a lot of things for granted, right? There's a certain style to proof writing, whether you're in kind of computational stats and machine learning or theoretical stats. There's often a kind of a community style and how things are done and why they're done a certain way. And if you're not aware of that, that kind of idiomatic approach, it can be difficult to follow along and what steps are skipped and why things are presented in a certain way. So it's not even necessarily just understanding the linear algebra better. It's kind of understanding that particular idiomatic culture in a given community. That can be very kind of difficult to wrap your head around. And some references take more for granted than others. And, again, there's a lot of heterogeneity and variation. But keep that in mind, right? That it's not just like, if I understand the linear algebra better, I'll understand the derivations of this paper better. It might really just be that you have to kind of write a few papers in that field, get a bunch of reviewer feedback or get colleague feedback, and then you start getting, you're supposed to do this. There's all these unwritten rules that nobody tells you about. And until you kind of get a grasp of those, a lot of stuff's just not going to make sense. Why is it done this way? Why is this result considered sufficient when it maybe isn't sufficient in practice? And you'll oftentimes, when you start digging into that, you'll start seeing the tension between some of those idiomatic perspectives and more applied perspectives. So in computational stats, for example, there's very, very rarely do you get a paper that kind of actively tries to break the method and identify where something fails and demonstrate it fails that way in exercise, in demonstrations and exercises, things like that. Instead, it'll be like, here's an asymptotic proof, and then here's like the one demonstration in a super ideal case where our thing is better than something else, some other benchmark that we've defined. And if you don't understand what a good benchmark is, if you don't understand when a demonstration is relying too much on ideal circumstances, if you don't understand when that asymptotic result is relevant or not, even if you understand all of the math, you're not necessarily going to be able to put that all together and connect it into applied practice. So I think it's often really helpful just to kind of like sit down and start with a project, right? An example of one that came up last year was I was trying to understand the asymptotic variance in Markov chain Monte Carlo. So you long story short, you have this sequence of states. You assume that they're jointly multivariate normal with a certain conditional structure, and then you want to understand what happens when we average over all those states. And there's a well-known result for the asymptotic variance. It's the sum of the paired auto correlations, or the auto covariances, really. And that determines things like your Markov chain Monte Carlo estimator error. And there's a bunch of kind of weird things that happen in that proof. There's the actual derivation of that result, and then there's how that sum over auto covariances is calculated. Because it's, in theory, an infinite sum. You don't have infinite terms in practice, so you have to truncate it at some point. And there's various truncation strategies and kind of debiasing strategies given that truncation. And then there's the actual method for summing it. And you can sum constructing the auto covariances before you sum them. There's kind of the naive approach, which is like a double loop. There's a slightly more efficient approach where you do these like Wilford accumulators and you do it in one loop over the data, or kind of like one and like a fraction loop. And then there's this fast Fourier transform approach. And most of the arguments for the fast Fourier transform approach have this really weird kind of indirect proof for why this result should be applicable, where they'll basically say in the continuous setting, if you have kind of a continuous sequence of states, think like a Fourier transform kind of setting, then you can compute something like this sum using a certain kind of combination of Fourier transforms and integrals. But we're talking about a discrete system here. There's no continuous setting. There's no we're not discretizing a continuous setting. It's always fundamentally discrete. So why would those continuous theorems have any application here? And as far as I was doing a bunch of research. I was looking at all these the signal processing books, going through the Wikipedia, and I eventually found that there is a completely another way of approaching this, that you can just directly show that a discrete Fourier transform, in particular fast Fourier transform, can approximate a certain circular sum, which ends up approximating, the FFT can calculate the certain circular sum, which can end up approximating the sum over the FFT can approximate these certain kind of circular calculations that approximate the lagged auto covariances. So you compute the FFT, you get all of those lags automatically, sum them up, great. But there's no proof for that result. So I had to dig in further. Eventually I was on the Internet Archive, and they have all of these old textbooks, these textbooks from like 15, 20 years ago, that you can check out. And by digging through those, I eventually found a few results, and I didn't really like the proofs, so I was able to then follow up and kind of prove it in a more direct way that I found satisfying. But I had to go through that whole chain of stuff, and it's admittedly a very minor point, but it was a very fulfilling task for me because I got to dig into all of these references, understand a broader scope of things, better understand the kind of separation between some of the theory here and some of the actual calculations and algorithms, better understand the robustness of this approach and when how to make it even better, and then an opportunity to kind of like flex some of my mathematical calculation skills a little bit. Doing nothing super fancy, just some kind of complex analysis calculations that I haven't done in a while. But it was just kind of nice to exercise those muscles. So I think things like that are often really helpful. Now, it can be frustrating, right? You don't get an answer immediately. You've got to dig, you've got to work, you've got to calculate. It often helps to talk to people and have a community to work with. And that's, again, that kind of networking aspect of going to academia. That's one of the benefits it can have, is you might get a cohort of people you can work with, which in of itself can be worth the process. Although you can go to an academic program and you don't get that cohort, and you might be able to develop that cohort completely independently. Finding a group online, talking with people on social media, on a Discord server, etc. So yeah, so like you can approach this from all kinds of different directions. Academic programs, masters, PhDs, those can all be great. Just go in being aware of what kind of the compromises are for that. You're not going to get paid. If anything, you're going to have to pay. So there's the opportunity costs. There's the direct costs. There's the risk of getting a bad advisor or getting a bad cohort. And so kind of understanding all of that stuff and being willing to accept that risk and getting something out of it, even if you don't get the ideal situation. But also just finding little projects to work on and kind of let that direct you. Find a little problem that sets a context, and you can explore that context without things being as overwhelming as they could be. Just like, for example, another one that I did recently within the last year was connecting singular value decomposition to PCA. PCA is often presented in terms of eigen decompositions. And sometimes it's presented in terms of singular value decompositions, but a lot of times there's not a direct connection there. Like, there's no proof showing why those are equivalent. So somebody had asked about that. What was the only problem I was working on? If somebody asked on the Patreon, and so I just dug into it, and it was kind of a nice opportunity to have this like very narrow context to understand. Okay, let's dig into SVDs a little bit better. Let's connect it to PCA. Let's make sure we really understand what's going on here from all these different perspectives. And then, that's like a new tool in my tool belt, something I understand better, and I can move on to something else. And that can often be helpful. These kind of like little projects can be more useful than to trying to like learn a proof or a derivation, because you're connecting it to not just the theory, but also the applied side of things. And that really kind of like builds up your foundation of tools that you can apply in practice. So yeah, I know I've been rambling a little bit. I know it's not necessarily a fulfilling or satisfying answer, but I think the unfortunate reality is there really isn't a universal way of handling this. There's no clearly best way to kind of build up your skills and find a good job where you can continue to build up those skills and be involved in engaging, fun activities. I've worked with a lot of companies that are kind of known for, you would expect you could do a lot of data analysis stuff there, and a lot of people there don't get to do anything fun. I've also worked with very small companies that do very, very practical applied things that you might never imagine have data people there, and they do really, really cool data analyses. So I think you want to keep a wide net, expose yourself as much as possible, try to build as much of a network as possible, both for finding opportunities and learning and asking questions and having conversation. Again, the probabilistic modeling Discord server is there, free to join. You can ask questions, you can answer questions, you can just have a conversation. So give that a chance if you're struggling to find other things. And when things get a little bit overwhelming, just try to find a little project to work on, and something that's like applicable to what you're already doing, and just go down that rabbit hole and try to kind of understand things better and just build things up iteratively with the context of that particular project. Try to make things a little bit less overwhelming. And if there are particular questions about certain kinds of academic programs or certain kind of jobs or things like that, just follow up in the chat or on the comments, and I can try to offer more precise guidance as well. All right, let's get into some stats proper. So JD's asking about retrodictive checks. So, as you might recall, if you've read any of my work, a posterior retrodictive check, or more particularly a visual posterior retrodictive check, is when you take some kind of summary of the data and you apply that summary to your observed data and to your posterior predictions, and you want to make sure they're consistent with each other. And if they're not consistent with each other, that means there's some kind of tension in your model. Your model's not able to reproduce the structure that you see in the data, at least in the context of that summary. And that can give you guidance on how to improve your model and improve its adequacy. Now, there's an art to choosing that summary statistic. And JD is asking here, what if you chose a summary statistic that you can think about as an estimator derived from the model structure itself? Is there a certain kind of circularity there? When you do that, are you always guaranteed to get a good answer? Are you potentially fooling yourself into thinking that your model is adequate when it may not be? So let's talk a little bit about retrodictive checks with some figures. So the first thing I want to emphasize here is the right construction of retrodictive check. So this is the wrong way to do it, and this is something I see quite a bit. I've had a bunch of questions about methods that are basically equivalent to this in the past. I think even Bayes plot might do something like this automatically, which is another Bayes plot sin that frustrates me to no end. So what you might do is have some kind of metric that's going to take observed data and your predictive data and compare them and give you some number. And then you could do that over and over again for all of your posterior predictions and then try to visualize that. That is not a proper retrodictive check. This statistic mixes observed data and predictive data, which might be useful for something that you want to do down the line, but it really doesn't define a proper retrodictive check or a visual retrodictive check. Instead, what we want to do is this. You construct a summary, you apply it to the observed data, you then apply it to all of your posterior predictions separately. You then find a way of visualizing the observed summary, and then a way of visualizing the ensemble of those posterior predictive summaries. Then and only then do you connect the observed data to the posterior predictive data for your comparison. So in the case here, the summary that we're looking at is the kind of projection onto, say, a covariate plane. So we can do a scatter plot for the observed data. We can be a little bit better here because we can interpolate our posterior predictions, and then we can compare them. Right on the top, we get nice agreement. On the bottom, we get disagreement. And the nature, the systematic structure of that discrepancy gives us a sense for what might be limiting about the model. So, for example, if this were a regression model, and we see the bottom plot here, that would clearly indicate that our location function isn't rich enough. It's too rigid. It's kind of able to capture some regions of the observed behavior in some region of the observed space, but not over the entire observational space. So, with that in mind, this procedure works for any summary. It doesn't matter how you derive that summary. So long as you apply it in this way, you will get something that serves as a retrodictive check. If the output of that summary agrees for both the observed and the posterior predictive data, then there's no indication of tension or model inadequacy in the context of that summary. And if you see a discrepancy, then there is something inadequate about your model. It does not matter what the structure, interpretation, or meaning of that statistic is. However, the interpretability of that summary dictates how well you can interpret the nature of that retrodictive tension. Right? So it's one thing to identify a discrepancy. It's another thing to be able to connect that discrepancy to your model structure and motivate an improvement to your model. So for example, if you have some kind of estimator-based summary, and the estimator is based on modeling assumptions that have no relevance at all to your model, then when you construct these retrodictive checks, the structure of your actual model that you're sensitive to might not be what you expect. So, for example, if you have an estimator that under certain assumptions would isolate the consequences of say, one parameter, but in your actual model, so your actual model is more complicated, so an estimator wouldn't isolate just that one parameter. So if you think it's isolating that one parameter and you look at the retrodictive check and you see agreement, you might naively think, oh, so that everything involving that parameter is fine. Or if you see disagreement, you might think, oh, well, clearly something's wrong with how I'm modeling the behavior around that parameter. But that's going to be misleading if you're relying on that estimator interpretation. So again, visual retrodictive checks work for any summary. The subtlety is how well you can interpret a failure, or in some sense, a success. If your interpretation of that summary and what information it's isolating depends on certain modeling assumptions that don't hold, they're in direct conflict with your actual modeling assumptions, or say you're making some assumption about the true data generating process, which doesn't end up holding, then your ability to interpret any kind of retrodictive tension, any disagreement, and connect that back to your model structure, that can be compromised. So it's it's a very subtle point here. Technically, the retrodictive checks are fine. How productive the retrodictive checks can be can very much depend on how well you can interpret the summary, which can itself then depend upon any modeling assumptions to go into the structure of that summary. So as an example, let's say that we're looking at an empirical mean. Now, under a simple model, an empirical mean might connect to a single location parameter, right? You think of an empirical mean, empirical average as estimating that location parameter. Now, let's say that your model is heavy-tailed, and maybe even the true data process is heavy-tailed, so that there is no true mean, and there really isn't a good connection between the location parameter and the empirical average. So say something like a Cauchy is notorious for. So you can always compute empirical average of the observed data and all your posterior predictions and compare these two things. But any agreement or disagreement no longer necessarily tells you anything about the behavior of that location parameter or the adequacy of that location parameter. So it can still, it's not necessarily a bad retrodictive check. It's not like it's lying to you or it can mislead you on its face. But when you try to interpret any tension that you see, that might be problematic. And one thing I should emphasize here, one thing that makes retrodictive checks or posterior retrodictive checks so powerful is that we're not just getting a point estimate for the predictions, we're getting this entire posterior predictive distribution. And so when we're comparing observed data to posterior predictions, we're looking to see whether the observed data falls within this distribution of posterior predictive summary behavior, as opposed to asking if it's right on top of it. So in the case like the Cauchy model, when you have a very heavy-tailed observational model, and you construct these posterior predictions, what's likely to happen is your posterior prediction is going to get super diffuse and just kind of wash out everything. And so there won't be any disagreement because your posterior prediction distribution just is covers everything. So again, the redshift check is fine. There's no, like it's going to do the right thing, but it's not necessarily going to be able to isolate the thing that you thought it was isolating. One way of robustifying the use of these retrodictive checks and avoiding a misinterpretation, which might cause you to go down a bad path in changing your model, is to not so much think about estimators as estimating a certain parameter, but rather as isolating certain kinds of behaviors. And this is one reason why I refer to these as summaries. So an empirical average and an empirical median, yeah, you can think about them as estimates of parameters in certain models, but more generally, you can just think about them as notions of centrality. Where is the data clustering? Where is the observed posterior predictive data clustering in the observational space? That interpretation is going to hold generally, whether or not that centrality estimates some parameter in your model. Another example of this, OBS out here, is in hierarchical modeling. One statistic I like to use when you have a relatively simple observational model with like a clear notion of centrality is an F statistic. So you can compute the empirical average and empirical variance in every group, and then you can do it's the average of the variances over the variance of the averages, and that gives you this F statistic. Now, in certain kind of ANOVA models, this F statistic estimates certain things, or it's used as a p-value with certain kind of guaranteed false positive and true positive properties. Rates. But more generally, you can just think of it as a measure of heterogeneity, of inconsistency across the groups. That absolutely holds, right? If behavior is homogeneous in every group and you have the same mean and you have the same empirical mean and empirical average, then the F statistic is going to be very close to zero, just by construction. You just go through the calculation and see what happens. And then as things get more and more heterogeneous across the groups, then the F statistic grows. So when you run your retrodictive check and you compare your observed value, which here is close to 12,000, and your posterior predictive values, which are all clustering very close to zero, it's clear there's a problem here. And we can connect that discrepancy to some notion of heterogeneity across those groups because of this general interpretation of the F statistic. Right? We don't have to rely on any modeling assumptions about estimation or anything like that. We're relying instead on this kind of general information summary, and then the discrepancy between the posterior predictive distribution, which might not be obvious here, but if you look really closely, you can see there's a distribution of those posterior predictive values here. It's just so close to zero relative to the observed value over here on the right. That discrepancy then tells us there's something inadequate about our model's ability to capture that heterogeneity. So I hope that roughly addresses the question, JD. It's admittedly a very subtle point, but I think one thing I want to be clear on is that when you do posterior retrodictive checks appropriately, they're quite robust, right? It's kind of hard to get this comparison between your posterior predictive behavior and your observed behavior and have that lie to you in some sense. The subtlety comes in when you look at that comparison and now and there's a clear discrepancy and you want to be able to connect that to how to change your model. That's where things can potentially go wrong. And that's where it helps to think about these summaries as summaries and ask what information are they isolating rather than estimators, where the connection of that estimator output to your model structure might depend on a bunch of modeling assumptions that don't hold. All right, so Jay's asking in the chat, but if you say your model was a Bayesian model, ANOVA, then use a frequentist ANOVA and a point F statistic compared to the posterior predictive for F is not circular logic. No, so I don't see where the circularity comes in. So if you have an ANOVA-like observational model, and then you happen to make it Bayesian, then your posterior predictive distribution for your F statistic is going to look like the observed F statistic, which makes sense because your or how, I don't want to say it. In that case, the observed and posterior predictive F statistics, the magnitude of that F statistic, you can connect to some notion of null hypothesis testing significance, or some precise notion of what that new number means. But posterior retrograde check doesn't rely on that. All you're relying on is that qualitative comparison between the posterior predictive behavior and the observed behavior. So there's no point for circularity to enter in here, right? You're treating the observed data and the posterior predictive behavior completely separately from each other. You're projecting them in the same way. And there's no way for that to then feed back. The only circularity or feedback is when you take that posterior predictive check and you potentially misinterpret any discrepancy or tension and how you go and change your model. So certainly if you were to look at a retrodictive check, you misinterpret the meaning of that summary and hence what that tension might mean, and you go and change your model in the wrong way, and then you don't ask any more questions, that could be bad. But if you go back and then you reevaluate that model and you see that that change hasn't in fact improved your retrodictive tension, then you know that your hypothesis about what that retrodictive check was telling you was wrong, and you have to rethink about what's going on, right? So there's always these safeguards built in that prevent that kind of circularity from happening. The only way to see a retrodictive tension and then reduce that retrodictive tension or eliminate that retrodictive tension is to improve the model to better match the true data generating process in the context of that summary. Right. So again, like if there's this a particular circularity that you're worried about, if there's a particular feedback that you think is problematic, let me know and I can try to address it. But in general, there's nothing that kind of cycles back without getting checked again. If anything, when you're using a summary that is based on modeling assumptions that also hold in the model and also hold in the true data generating process, that just means that your the retrodictive checks based on those summaries are even more interpretable than they might be, right? Instead of thinking about a general notion of centrality or heterogeneity, you can have precise notions of the parameters that determine that centrality and heterogeneity. And then you can go directly try to modify your the model around those parameters. So if anything, things get better when you have all of that agreement. But there's no way for things to get masked or misled, right? And that's the real power and robustness of posterior retrodictive checking. There's no way to have if your model agrees with the true data generating process, there is no summary that will construct a observed behavior and a posterior predictive behavior that disagrees. If there is disagreement in your model and the true data generating process, then you might construct a summary that is not sensitive to that disagreement. to that inadequacy of your model. And that's why we never interpret a positive retrodictive check to mean that your model's right. It just means that there's nothing that's being isolated in that summary that is indicating any kind of problems. And that's why you always want to keep them in mind about new statistics going forwards or new summaries that might identify a behavior that you had overlooked or took for granted previously. Right. Yeah, but feel free to kind of continue the conversation in the chat, and I'll come back to it as we go. All right. Next round of questions from Zach. First one. Any advice on how to approach meta-analysis from a neurodegenerative perspective? So I have written about this a little bit in my prior modeling chapter. So meta-analysis is weird in that a lot of the meta-analysis you see in the literature, especially in things like psychology and social sciences, they are based on, they're very much like a lot of statistical analyses in those fields, where it's just, here's an estimator, let's not ask any questions, but the assumption goes to that estimator, we apply it to the data, we get something out, we assume that's telling us something useful. And because of that, a lot of inferences and analyses are bad, but so too are the meta-analyses, right? They don't actually do anything useful. It's, you know, you're trying to like identify a problem, flaws in the analyses with another flawed analysis. That's circular. That's bad. So the way I like to think about meta-analysis is to, think about the outputs of all of these different analyses as data, as observations. And what you're modeling is the data generating process that gave rise to those observations. Right? So when you look at, say a reported result is given by, some central value in some kind of error bar. And every field is going to, when you say like it's, 0.5 plus or minus 0.3, whether you're in physics or social sciences or particular social sciences, biology, they're all going to have different conventions for what that plus minus means. So keep that in mind. And so we want to think about those results not as inferences, not as parameter constraints, but rather as observations. And so we can then ask, well, how can we connect those observations to the parameters of interest in our model? In other words, what is that data generating process that goes from parameter or behavior of interest to the output of those analyses? So a particularly simple model might be if we trust those analyses to be reasonable, and we think that those results are all potentially noisy, but they are not necessarily unfaithful or biased representations of what actually happened, or the unfaithful or biased summaries of that behavior of interest, then we might kind of approximate the data generating process as the common behavior of interest, and then in this case just a normal, with the reported result as the data, and then the measurement variability, we can just take to be the quoted variability. And the CN here is accounting for that potentially kind of different interpretation of what that plus minus means. Is it 1 sigma, 2 sigma, 99% quantile, 95% quantile, etc.? And so depending on all each of those in particular interpretations, we can tune the C to be the right value, and we get this kind of consistent model. Now we can also treat the kind of quoted uncertainty as data as well. And so we have not only a common behavior of interest, but we have the kind of true measurement variabilities, which maybe is fixed across multiple experiments, or it's fixed across groups of experiments. And then we have a second part of the observational model for how that variability arose. Now, these models here, they're relatively simple, right? And that's fine. Like all these meta-analysis statistics that are out there are all basically assuming a similar kind of structure like this. They're just not making it explicit. Here we can actually think about common behavior, generating all of these different observations through the analyses that have been reported. And we're assuming here, in both of these models, in both of these or all these data generating processes, that these analyses are relatively trustworthy. But the nice thing about this approach is that we can just as easily accommodate potential bias. So if we think that there are certain analyses or certain analyses from certain groups or certain kinds of analyses that might be systematically off from what everyone else, not only what everyone else is doing, but also from this kind of underlying behavior of interest, then we can always have, instead of just theta here, we can have theta plus some offset. And that we learn that offset along with theta, right? So we can kind of learn a tension across all of these different analyses. And maybe your prior model for that tension is heavy-tailed. So we kind of encode sparsity in that. Maybe even a sparse hierarchical model. So you try to cluster as many of the experiments together as possible while allowing for some of these outliers. And this does two things for you. One is it helps kind of disconnect your inferences, your meta inferences for this behavior of interest from any problematic analyses, but also identifies which of those analyses are problematic. Are they biased? In a case like with here, if you add a little bit of flexibility to this model, you might learn how some groups under or over-report their uncertainties. Right? Now, these kind of analyses are always very politically difficult, because the second you start learning who's good and who's bad consistently, that's awesome for the actual goal of meta-analysis. But then to report that meta-analysis, you have to say why you're not including some of those results, and saying, look, they're clearly inconsistent, or they're inconsistent with the other results, or not even internally self-consistent with itself. It doesn't matter how systematic or how principled you are about it, or how people are going to get offended, and it's going to be a political quagmire. So it's always kind of challenging to do it, but it's totally feasible, right? And all you have to do is think about all of these separate analyses as individual data generating processes. What they're reporting is the output of that data generating process that you can think about as metadata. Even if they're claiming that, like, we did a Bayesian analysis and here's our posterior mean plus minus a posterior standard deviation, right? It doesn't matter how they get that, whether it's frequentist or Bayesian, you're going to treat it as data in the context of the meta-analysis. And then your data generating process is how do you go from this common behavior of interest to those meta-observations, to those analysis outputs. And it can be as simple as assuming, a model like this, where you assume that the kind of quoted estimates cluster around the common behavior of interest. Or you can allow for additional flexibility. You can add biases and offsets. You can model those biases and offsets hierarchically, or with sparse, particularly with sparse population models. There's a lot of kind of fun things that you can do here to try to separate out the trustworthy results, or the consistent results from the inconsistent results. And not only get a kind of a sense for how to construct a better estimate for this common behavior of interest, but also identify things that might be off. Another nice benefit about this can then formalize a lot of heuristics that are already in place. So for example, in physics, there's this CODATA working group, and they're effectively doing this, just not explicitly. Right? So what they'll do, so there's something like this, I should say. They basically treat these CNs as parameters almost. And so if there's inconsistency across a group of quoted measurements, what they'll do is they'll inflate the uncertainties on all of those measurements until things agree, right? And that sounds kind of weird, and in some sense it really is. But you can interpret that as a meta-analysis where you're kind of allowing the quoted uncertainties to be kind of systematic underrepresentations of the true uncertainties, and then you try to learn the uncertainties that would give you consistent results. That isn't necessarily the right model. Personally, I would lean more towards the biases that are unreported than just inflating the variations. But they're both valid data generating processes, and by treating them as such and being open about the assumptions in those data generating processes, you can now have a principled discussion about which of those approaches might be more appropriate for a given meta-analysis. So there's not much more here. I'm just kind of talking about some of those possibilities. But yeah, it's really as simple as you treat the analysis outputs as data. Your data generating processes that you now want to model is that bridge, that connection from the common behavior of interest to these individual observations, meta observations, including all of the heterogeneities, the idiosyncrasies in those individual experiments or kinds of experiments. If you're worried about bias, throw in some offset parameters. If you're worried about overrepresentation of uncertainties, throw in some scaling parameters. These CNs, and learn them with everything else in the meta-analysis. And then just be careful about how you quote your results as to not try to single any individuals out who, when it might not be politically advantageous to do so. I haven't done a lot of meta-analyses myself. And so I'd love to see examples of kind of thinking about meta-analysis from this data generating perspective. So if anyone's done this or does it in the future, let me know. I'd love to kind of see a lot of these heuristics that are already used in meta-analysis formalized better from this perspective, and see how we can do even better on that. All right, so the second question seems to be an unending flow of stats literature dedicated to the new causal inference methods. Whew, boy howdy, isn't there? After reading your stuff over the years, I can help but think that much of the literature reflects a general willingness to simply model data generating process. Couldn't agree with you more. And he's come across multiple papers that boast of model-free inference. Oh, that's another. You're just hitting a lot of points that I'm both agreeing with and also just pain me and how true they are. Your work makes a strong positive case for probabilistic modeling. Do you see a need for complementary, more competitive approach of demonstrating the pitfalls of overhyped methods? If so, is there anyone you think does particularly well? All right. So let me kind of tackle this piece by piece. I'll just briefly, for model-free methods and model-free inference, this is I hate this so much. People get so uptight about this. There's one person on social media a few years ago who is now a professor at a very well-regarded university, and claims to do Bayesian inference, but is basically just doing, kind of like slightly generalized regressions, assuming no confounding, doing all of the classic regression stuff, but then adding a little bit of generality so that certain kinds of estimates are slightly less sensitive to the modeling assumptions for the location function, right? Still extremely sensitive to assumptions about confounding, still extremely sensitive to assumptions about the heterogeneity, the kind of variation around the location parameter, and things like that. But because there is kind of one assumption that you're a little bit less sensitive to, it's now presented as model-free. And they unironically embraced that position and didn't think any of these other assumptions were at all realistic or meaningful or relevant or whatever. And I just don't know. When you get to that point, it's hard to have a conversation with people. Nothing is model-free. You can make your model more flexible or more general. That doesn't make your model assumption free. Nothing is assumption free, especially without infinite data. It just doesn't work like that. So that's absolutely. I think you see model free, it's a warning sign. It's a red flag. There be dragons. Proceed with caution or run away. Causal inference stuff. Yeah, I think my perspective on causal inference, my kind of like politically incorrect perspective on causal inference, is very on one hand, as you said here, Zach, that it's just people who refuse to model the data generating process. And the frustrating thing about that is there's kind of a token appreciation of data generating processes. People refer to data generating processes. They'll draw diagrams that kind of like get close to a data generating process, but then they don't go all the way. They don't actually use that. They just end up with a regression. And so the kind of the flip side of that also frustrates me is that when people talk about causal inference these days, 99% of the time, it's just they still end up using a regression. They talk about a lot of stuff, but it's either to try to identify when a regression is okay, or force a regression anyways, even if it's not okay. But they never go away from a regression. So it's there's nothing general about it. You're not modeling causality. You're just trying to like add more bells and whistles to regression without really rethinking the whole structure of regression. And so when you're always bound to regression and you're just trying to like infinitesimally move away from it, you're never going to get very far. And I think that's why there's such a paradigm shift of not just acknowledging that a data generating process exists, but modeling the data generating process. That's where, in my opinion, things really become productive. And so for those who haven't seen this, I have this post on Patreon. This is public, so anyone can read it, where I go through this kind of classic paper from, I think it's Sanderson and I want to say Westmoreland. Can't remember the authors, but the link is here. And they kind of go through, here we go. Yeah. Greenland and Westrike. And this is like a classic paper that a lot of people go to for what causal inference is. And what they basically do is they start with this diagram here. This is sometimes referred to as a causal diagram, or they'll call this a data a DAG, a directly acyclic graph. But note that it only includes observed variables. And then the arrows are kind of capturing the correlations in the observed data. So when you have directions on the arrows and not just lines, presumably you're making some argument those correlations are induced by causal changes, right? A change in smoking propagates and then affects a change in stroke, a change in HIV, etc. But what this doesn't tell you is what is the model for those changes? How does smoking affect stroke? How does smoking affect HIV? And then how does HIV affect stroke? So there's a lot of stuff that's missing here. And then when it actually comes to the analysis, they just jump into a regression. So they just take this and then they just add, effectively a two-stage regression that they collapse into one. But that's it. That's all it is. It's just going back to regression. It's just trying to find another way of rationalizing regression models. So I look at something like this and I just go, why is it still a regression? The jump from this diagram to a regression is making a giant number of assumptions. You're taking those assumptions for granted. And that's really dangerous for the validity and robustness of your analysis. So for me, the way, this kind of paradigm shift where I think you make this much more productive is sure, start with this DAG if you want to, but think about it as an actual probabilistic model. This is representing a conditional decomposition of the joint distribution of all of these observed variables. And now you can start thinking about these individual conditional distributions and how you might want to model them. Right, so here's your kind of individual pieces, and these are now components of your model that you can reason about individually and for snapping together into a consistent joint model. But there's still the problem that you're not kind of, like, in order to actually construct these predictive models here, you need to be able to model the underlying behaviors. What's causing this interaction? What's causing this coupling between age and stroke? Right? What's the strength of that coupling, etc.? Is it linear? Is it nonlinear? And this is where a lot of people struggle. They'll read about causal inference, and this happens a lot in my consulting engagements, for example, or somebody has read McElrath or any of the other causal inference references out there, and they'll draw a DAG, and they get really excited about the DAG, and they go, okay, great, I've done the work, I've got the DAG, now how do I do this in Stan? And I just have to say, you can't do that in Stan. There's not enough information here to put this into Stan. If you want to put this into Stan, you need to specify what those underlying models are, and that means introducing parameters. And this is a big difference. The kind of DAGs that I advocate for and the kind of DAGs you see in causal inference. When I talk about a DAG or a graphical model, I want both the parameter, the model configuration variables, and the observed variables in the same graph. So I not only want to understand what are the interactions between these observed variables, but also what's moderating those interactions. If it's linear, what's the intercept and slope? If it's not linear, what kind of functional form do you have? And what are the parameters that configure that functional form? So by thinking about DAGs as a joint model of not just the observed variables, but observed variables and all of the model configuration variables, and then breaking that down into these individual pieces, this is what puts us in a position where we start thinking about building little probabilistic modeling components and then packing them together into a consistent joint model. And what I love about this is that when you take this perspective, a lot of things just become trivial. I don't like to use the word trivial. Trivial is a super condescending word. When you're reading it, you know, when you don't know any better and you're just reading through, you know, some kind of reference and somebody says something is trivial, even mathematically, when trivial means, like, there's a very technical definition for it, it comes across as super condescending. It'd be off-putting. So it's one of those words I try to avoid. So I'll use instead things like straightforward or, you know, immediately implied by the assumptions or, you know, whatever it might be. But some things really do become obvious and trivial from the right perspective. And one of them is confounders. So the reason why confounders get so weird from this classic causal inference perspective is that it requires you having unobserved and observed variables together in the same graph, which is weird and kind of anathema to that classical picture where everything is supposed to be data. So when you have this confounder U here, and everything else an observed variable, how do you interpret U? Well, it can't be a parameter because you don't show parameters anywhere else. And this is where you get these, like, really weird contorted interpretations of things like confounders are unobserved data or missing data, or they're things that you could observe but you didn't. Like, well, none of that matters. You didn't observe it. Don't talk about hypotheticals here. The data generating process didn't include it as an output, so it's not part of the output of that data generating process. That's not part of the predictive distribution. Sorry, it's not there. You can't just pretend it's there. But when you treat this from a kind of a joint modeling perspective, and you have the parameters, the model configuration variables, as nodes already in your graph, then adding confounding is trivial. It's immediately straightforward. There's no obstruction to it. There's nothing weird about it. There's no hurdle in incorporating it. It's just another parameter that you're adding. Yeah, it makes your model more complicated. Yeah, it makes some of these component pieces more sophisticated and a little bit trickier to model. But that's what you need to do in order to incorporate that behavior. And you can look at this graph, and now it's so much more interpretable, right? We have all of the interactions that we need to understand. We can isolate all these individual component models, these kind of individual observational models that we need to think about. These components of the data generating process, and we can reason about them individually, and then the structure of these models is then what goes into a probabilistic program and builds up your say your stand program, builds up your code, right? So to me, this is just like I look at something like this and I'm lost. I don't know what to do with this. There's so much that's unsaid here that I can't turn this into a Bayesian model or do an analysis with this. This is not enough. It's even worse when somebody has a plot with like 30 observed variables and there's arrows between everything. I'm sorry, I can't do anything with that. That's a complete mess. But if you can do the work and you can construct something like this, now we're talking, right? This is now something that we can start breaking down into more manageable pieces, really digging into what the underlying assumptions we want to make are, make those assumptions either mathematically or in code, and then build up our model and have that complete specification that we can then plug into stand, hit boop, go, and everything comes out consistently. Right? That's the other nice thing about joint modeling and Bayesian inference is if you build the right joint model, there is nothing weird you have to do to handle confounding or backdoors or all this weird stuff. It's just write down the data generating process, build the joint model, condition on all the observed data at once, and your posterior inferences will self-consistently incorporate all that information, take into account all these complicated interactions all at the same time. It's magic if you've done the work to build that joint model. But going back to the last part of your question, Zach, of is there a need for a more combative approach to demonstrate the pitfalls of these methods? I don't know. On one hand, the kind of vindictive side of me wants there to be that. Because so many of these methods, as you say, they're overhyped, they're fragile. People don't use them right because they're not presented clearly. It's so hard to use a tool appropriately when you're not informed all of these important things about the structure and use of that tool. On the other hand, I just have not found combative discourse to be at all productive in practice, especially in statistics. Whether you're talking about trying to change people's mind in statistics in general, or applied statistics, or academic statistics, or any kind of scientific field, showing up and saying something's wrong. It doesn't matter how clearly wrong they are, right? In computational stats, it's happened all the time. Somebody would write a paper that, say, would generalize HMC, and they would do it in a way that completely compromised the reason why HMC worked and scaled. And not only so it's super easy to spot, but you can also then immediately determine the consequences of that. You can say all right, we'll do this experiment, and you'll see this behavior. And they might even have done that experiment in the paper, and you can point to it, go look, it's clearly showing. Instead of working in hundreds of thousands of dimensions, it's failing in 5 dimensions because you changed that one thing. It doesn't matter how logical or precise or mathematical you can be about that. If you are combating, if you're coming in and critiquing a paper, and the authors don't want it to be critiqued, they're going to go on the defensive. And they're not going to listen to anything. And a lot of people in academia have their self-worth, have their esteem, their academic, their professional esteem, coupled to their papers and their academic work. And when you critique their work, a lot of people internalize that as a critique of themselves. And they get hyper defensive, a reactionary defensiveness because of that. And I don't mean, that's not like oh, those people are bad because they have that. Everyone in academia has that. I've had that forever, and I probably still have it. No matter how much I try to deprogram myself, it's super unhealthy to have that attitude. But it's just what academia does to you. It just builds that into you. So I've just I don't think there's a lot of productivity to trying to attack these existing methods. What I have found to be most productive, and it's frustrating because people are wrong. People are like, it's not even like people have different opinions. People are not being consistent within their own assumptions. They're violating their own assumptions, right? It's a clear wrongness, and people are suffering because of that. People are using these methods, not knowing that they don't work, getting bad papers and analyses out of that is going to bite them later. Or worse, people who really care will dig into them. They'll see some of these inconsistencies, and a lot of them internalize it as that they're using the methods wrong, not that the method itself is wrong. And then they get frustrated and don't feel good about themselves and the like. Right? It sucks. I get there's a big part of me that wants to be competitive, wants to go on the offensive, because people are suffering because of this. In a relative way, right? Of course, the world is messed the hell up right now. But relative to these particular things, it's not an overall healthy, positive thing in my opinion. But when you try to do that, it doesn't help. It doesn't make anything better. All I found to be productive is to offer an alternative, is to present a different perspective, show how this perspective can be more useful, show how other methods can fail while these methods are useful, not as a combative technique, but just as if you've been frustrated, if you've seen these issues before but don't really understand them, here's an explanation for why, and here's how you can potentially do better. And it's super frustrating. Again, it's like super frustrating to do that. But I don't know of any other better way. So far in my career, it has proven to be the most productive approach. That you just have to wait for people to find the problems themselves. Don't worry about trying to convince people who aren't going to get convinced for whatever reason. Are kind of stubborn because they don't understand things enough, or they're stubborn because they're too, their steam is too tied into their work, or they prioritize getting a quick answer out rather than getting a good or robust answer out, etc. Whatever it might be, right? There might be okay reasons for what they're doing, but it's just different to what you want. You're not going to convince those people. You can try to convince people on the boundaries, but that's going to then require a very kind of targeted approach. You have to identify, all right, where is this person having questions and doubts? How can we directly address those doubts and then bring them over to the perspective we think is more useful? And that's just a ton of work, right? I can do that one-on-one. I can do that at a party. I've done it at multiple parties. You can do that at a conference. You can do that at a workshop, right? But it requires that kind of one-on-one interaction. And that doesn't scale. So what does scale is providing those resources, providing that documentation, so that when someone kind of recognizes there's an issue and they search for, is this a problem? Is this me? Is this something that's out there? They can find your work, and find some relief, find a better way of doing it, and then maybe then continue to use the methods that you're proposing. So there's a certain kind of like, morally you want to go on the offensive and you want to be combative, but it just doesn't. I just don't think it's going to be productive ever. So instead, I think it's best to just like wait, spend as much time as you can preparing the material, preparing the documentation. And this holds for everyone here. Like if you're in your particular field and you're frustrated that more people in your field aren't doing it the way that you think it should be done with this kind of narratively generative probabilistic modeling perspective, then come up with case studies and example analyses and come up with a lot of this material. So when somebody searches causal inference in such and such field, your stuff might show up, and they might get this perspective they haven't seen before and get really excited. And now you have a new collaborator, a new colleague, a new member of the community that you can build up on. So it's what I try to do, and it's what I recommend for everyone else as well. Don't try to be, don't try to necessarily directly attack things. Try to be a little bit more constructive about things, right? And that's what I've been tried to do here in this Patreon post, where I'm critiquing that paper, but it's more of here's the alternative. Here's what I think is a better approach, and then I'm not sending this, to Sandra Greenland and Westrick. I'm not sending it to other people in statistics who like that kind of causal inference approach. I am putting it out there, sharing it with people, my community who might find this interesting, and then letting people find it organically when they're ready for it. And now they have a jumping off point where they can get excited about this stuff, and then potentially, then follow up on the covariate paper, and then that leads to other references and so on. All right, so sorry, a lot of questions here in the chat that I've missed here. All right, G, I'll come to the retrospective comment in a second. It's hard sometimes to know where to put little notes like this, right? Sometimes people will call my book chapter drafts blog posts, which I find a little insulting, because it's like 20,000 words and takes like weeks and months to put together, as opposed to something you just write in a day. So most of my blog post like things I put on the Patreon, and some of it's public, some of it's not, and I try to make it as clear as possible when things are public. But yeah, this is here, and if you haven't seen it before, take a look, and definitely share it with others. It's public. It's here for anyone to look through, if they might be interested. So JD's saying it's much easier to just write the joint model than get into all the rules about backdoors and colliders and the like in this kind of regression perspective. And that's exactly it, right? Like colliders and backdoors, this is what happens when you've built a model and then conditioned on the data, and then you're going backwards, right? Don't condition on the data until you have a model you trust, right? The reason why backdoors and colliders and all of this kind of causal inference stuff is so weird and counterintuitive is because you're literally going in the wrong direction. You're going against the data generating process. That's why things don't propagate in a consistent way. That's why things kind of, there's all, literally backdoors, all these kind of indirect ways of something interact with something else. When you instead start from the behaviors of interest and build up to the output data, and you incorporate all of the interactions and couplings in that forward process, all of the inferential couplings due to that, those kind of forward couplings are going to happen automatically. Bayes' theorem will handle colliders and backdoors and all that stuff for you. If you've built the right model, when you plug in the data at the very end, everything's going to happen in the right way. I promise you it's going to be okay. Bayes' theorem is magic in that respect. And that's a hard thing for people to kind of get over when they're not even aware. There might be, again, some kind of token discussion of data generating processes, but it's only ever really used in the regression context or as like a slight generalization from a basic regression model. There's never a kind of a stepping back and starting from the data generating process and then seeing if you end up with a regression or seeing if you end up somewhere completely different. So that even though there's a lot of kind of commonalities, some of these things that we're discussing, just the difference of going from forward, from behaviors to data, rather than backwards from data to behaviors, that paradigm shift is huge. And a lot of things simplify when you can make that shift. And it becomes easier to think about the joint model, which is what you're going to plug into Stan. You don't write an estimate in Stan or an estimator in Stan, you write the model. So if you want to do Bayesian modeling, you want to do Stan programming, you've got to understand what that model is. And that means not thinking about something like this, but thinking about something like this, and understanding what all of these probabilistic pieces are, and what their mathematical structure is, And this is all facilitated by thinking about that forward data generating process. It's a starting with that, right? You're not. It's the core of the entire analysis. All right, so Michael's got two questions here. I'm gonna do your first question in a second. I'll start with your second question here. Michael's saying that his brain kind of breaks when he tries to incorporate the idea of observational history from a neurodegenerative point of view. All right, so I'm not. Correct me if I'm kind of interpreting your use of observational history here wrong. I'm just thinking about it as like the history of where the observations come from. So let me know if I'm misaligned with what you're thinking here. It can definitely be overwhelming to think about the data generating process, right? It's one thing to be like, oh, a data generating process exists. There's this big complicated mechanism that goes from certain behaviors of interest up to the output data, and it's overwhelming to think about that entire thing, and that's absolutely true. However, I think what's overwhelming is building a big joint model, not necessarily thinking about that process. So where people tend to get obstructed a lot, they get stuck, is they don't know how to like write the stand program directly. They don't necessarily know how to write the full DAG like this here on the screen, and they just get kind of stuck in this, and they don't know where to go. But if you step back and you ask them where their data came from, it's often a much easier process to reason about. Where I see this a lot is I'll be interacting with colleagues or potential collaborators. One reference thing I'm thinking of in particular is kind of psychology, cognitive science, where I was speaking with a grad student who didn't have a lot of stats background, didn't have a lot of stats training, wouldn't know what a joint model is or how to build one. But they were responsible for collecting the data, and at the end they were doing a very simple model, and they wanted to learn how to make that model better and generalize it. And they were, kind of thinking about, all right, what math do I add to this model to make it better? Which is the wrong question, right? I needed to know what their data generating process was. And so I just sit down and said, all right, well, can you explain your measurement? And for the next 15 minutes, I got this detailed breakdown of, all right, so we have these individuals, and we think they think this way. And then they're interacting with this cognitive exam. And then this thing happens, and this thing happens, and this thing happens. Now, we don't quite understand what this and this is, so there's two possible contributions to the data. And they just described this intricate data generating process. And this happens over and over again. If we just step back and ignore all of the baggage and all the things we've tried to do in the past and just ask, where did the data come from? Answer it at whatever level of sophistication you feel comfortable with. That's where you start. You might have a simple story. You might have a very complicated story. Wherever, just start with a story. And then you can build up on that later on. Either adding kind of conceptual complexity or adding mathematical complexities or translating that story into a probabilistic mathematical form. So it really, and this not just works when I'm interacting, with other people. It's the same question I ask myself when I'm coming to an analysis. What is the data generating process? Where is the data coming from? And it's a brainstorming process, right? You're telling a story. All right, so this happened, this happened, this happened. Oh, you know what? As I think about it, then this thing also might have happened. Okay, and then this thing could have happened, or then this thing happened first, and then all right, you're just building that story up. You're brainstorming about the narrative. And if you're not familiar, I talk about these general techniques in this chapter here, which is all about thinking about probabilistic modeling as storytelling. You start with a conceptual story, and then modeling is all about translating that story into math, almost if it's like a foreign language. You start with the story, now how do we translate that into this mathematical language? And then using this storytelling perspective, start kind of formalizing a lot of heuristics and techniques that you might already be using. Some of which include things like starting with a very broad story and then making it more detailed. So you start with kind of a high level story, and then you take the pieces of that high level story and break them down into smaller stories. And then you break those pieces down into smaller stories. That's often very helpful. Alternatively, it might be more useful to start with a very detailed part of just a very detailed story of part of the data generating process. Right? If you're being overwhelmed by the entire narrative, just start with just one piece and build up until you have the whole story. On the other hand, if it's the details that are overwhelming, then start with a very crude story and add detail and sophistication, refine that model as you go. Right? And these diagrams are both, so the top one here is starting with a very fine detail in a small context and then expanding that to the full model. And then the bottom is starting with a very crude story and then iteratively refining it until you have the level of detail that you need. So I highly recommend taking a look at this chapter if you haven't before, to kind of like get some ideas for how to think about the data generating process and how to break it down into pieces and that are more manageable to reason about. The other thing that can be really helpful is in my probabilistic modeling and statistical inference chapter, I talk about the kind of conceptual pieces that go into a data generating process. And the way I like to organize things is in terms of phenomenon, environment, and probe. So usually there's some behavior we want to learn about. That's the phenomenon. That's the thing that we want to learn about. And unfortunately, we can't interact that phenomenon directly. Right? The phenomenon is going to exist in some environment. And when we try to observe that phenomenon, we're also going to end up observing that environment. The environment can corrupt what we see. But the phenomenon environment are still not the whole story. Because when we try to observe something, we try to interrogate this system, we're going to do it with some kind of probe, some kind of measurement, experiment, observation, etc. And that probe is going to have contributions of its own. It might corrupt or contaminate this system. We might end up only seeing part of the system and be some kind of selection bias that goes on. And if we want to build up a model of a data generating process, we have to include all of these pieces. And so a lot of times people will get kind of like, they'll overemphasize just this underlying phenomenon and take for granted the environment and the probe. This happens a lot with like regression models, for example, where people think a lot about the location function, but then the scatter around the location function or the sort of confounding, that's all just kind of taken for granted or ignored. It's also helpful for thinking about things like joint modeling of different observations. So when you have different observations that come from different data generating processes, how can you combine them together? Because each of those different data generating processes are going to be sensitive to different probes, different parts of the environment. And so even if they're sensitive to the same phenomenon, even if they're capturing the same behavior of interest, you're going to have to model those data differently because of all these other differing contributions. And so this is just a nice, helpful way of kind of starting to think about things. If you're really overwhelmed about where the data comes from, step back and think about what's the phenomenon, what's the environment, what's the probe, and then start filling in those details. And then finally, this idea of kind of an iterative model development, where, especially when we get overwhelmed by the details, so we start with a very crude story, a kind of an overall arc, and then we refine that story and add more detail. The kind of mathematical side of that, where we have a mathematical model of that crude story, and then we refine the story and we refine that mathematical model at the same time. I talk about that in my workflow chapter, which is all about trying to kind of systematize that process. How do we take an existing model, critique it, identify that we need to make it better and refine it, and then not just that we need to refine it, but how can we refine it to make it better? Whether that's improving the prior model, the structure of the observational model, changing our computational tools that we use for the analysis, changing the data process itself if we're not getting enough information, and the like. And so this kind of tries to formalize that. And in the end, I kind of talk about, kind of whole systematic workflows where you kind of start here and go here, 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 and here. This is pretty old at this point, and it's overall totally fine. But there's definitely refinements and improvements. Speaking of iterative refinement, that, for example, is in my teaching material that I have not yet had a chance to improve here. So a lot of new figures and ways of thinking about things to kind of really reinforce these ideas. But if just I'm not sure what you may have seen, what you haven't, but I would definitely check out the probabilistic modeling statistical inference chapter, especially the first section here on probabilistic modeling, and then the entire generative modeling chapter. And then I would take a look at the workflow chapter to really kind of systematize all these things. But the number one thing to start with is, where did the data come from? The story, conceptual, completely conceptual. Once you have that, now you have something to build on when it comes to your mathematical modeling. And hopefully, I think I kind of, as part of that, I addressed the first question about how I think about starting simple and iteratively add in complexity when modeling. Oh, sorry, this is particularly when modeling a series of points in time. So this one, the problem of modeling points in time is not a full data generating story, right? There's so many things that could be happening here. You have a system. It's apparently dynamical because it's changing. It's evolving. Okay, but what's changing? What's evolving? Is it some kind of location, some kind of centrality, and the data's following that centrality changing? Or is the variation of the data also changing with time? What are the dynamics? Are they defined by some kind of infinitesimal dynamical system, like a system of ordinary differential equations? Is it defined by an autoregressive process or a diffusive process? Is it defined by or more global picture, where you think about it like a Gaussian process, where it's more of like how much can things change over a certain amount of time, as opposed to what's driving that change? So all of those different perspectives suggest or motivate different ways of approaching the modeling of that time dependence. What I often like to do is start with a model first, and then identify the behaviors that are dynamical and changing with time, and then kind of replace, say, single parameters with time-dependent models. And that's one approach of taking it iteratively. First iteration, no time dependence at all, and then add more time dependence as you go. Although sometimes it's more natural to start with the time dependence itself, and then the right way of thinking about how to start simple and refine it is going to depend upon what your perspective is, right? If it's if you're pretty confident there's some system of ODEs, because it's, say, some kind of mechanistic model for your system at hand that everyone in the field uses, then you start there. And if you realize that the time dependence isn't flexible enough to capture what you see in the observed data, you might add more complexity to the system of ODEs. You might add interactions or nonlinearities. Or maybe you take your ODE solution and then you add a Gaussian process around that to capture any kind of residuals. And you argue there's some kind of like driving dominant system, and then there's some kind of contamination or corruption, some perturbation around that you're going to model with that Gaussian process. Even though you don't necessarily know what's driving that residual process, you can soak it up and allow and kind of get a sense for what is the kind of crude evolution, and then what are these finer details. But if you're thinking about this from an autoregressive perspective, you might start with an AR1 model and go to an AR2, 3 model, or we'll go to a moving average model, right? There's all kinds of different ways of expanding, depending upon how you're interpreting those dynamics and that evolution. And this all goes back to, what is that data generating story, right? I don't need, and when you talk about what is that data generating story, there is no correct level of detail. It's the level of detail that's easiest for you to think about. So if things are overwhelming to you, back up. Just keep backing up. Where's the data coming from at a very high level? then dig into it, or thinking about the pieces. What's the phenomenon? What's the environment? What's the probe? What's the structure of those? And how are they interacting coupled to each other? And then dig and refine that. And that's really what guides that. So I do have all of these case studies, and a lot of these do show that iterative process as well. In particular, the race case study definitely has, and this is with real data. I love this case study. I think like 3 people have mentioned they actually kind of know the context of where the data comes from and the particular application. But I love it. It's so good. It's so like niche me. It's fantastic. But it demonstrates this kind of iterative model building, and starting with a relatively simple model and then adding complexity for all kinds of different structure, important behaviors and contaminations and heterogeneities, and then ending with some really cool, sophisticated predictions. The movie review does have a little bit of iteration to it. This is also based on real data. So that'd be worthwhile to look at. But I would definitely, I think the race outcome one is where I would start. I think that's kind of the most complete one with real data. And then with the tree diameter growth one, it's a little bit simpler, but has a little bit of demonstration of iterative model building. The inferring customer conversion and the inferring fertility, these are both based on simulated data, but they are kind of designed to demonstrate iterative model building. So they're a little bit less compelling because they're using not necessarily real data. So there's not any kind of surprises that I didn't know or didn't kind of engineer into the process, but they still might be a very helpful demonstration of what's going on. And of course, the workflow chapter itself also has a demonstration in it that shows some kind of crude example, a simple model, and then building that up through a few different iterations. In this case, 4 iterations in total. And then some of the other case studies do as well. I think do I still have the hierarchical modeling chapter open? Yeah. There's a bunch of examples here. In section 4.3, I guess there's just the one. This also has some iterative model building in it. So it's a lot of examples. So take a look at those if to maybe inspire you to think about kind of how to think about your data generating process. All right, so let's see. So I had this one question from JD going back to the retrospective checks. So I guess it would just seem like a really useless check when the F statistic from the frequentist would likely agree with the F from the Bayesian analysis. It does seem like a critique. Well, again, it's a question of what's a useless check. Like, it's not a wrong check. Maybe it's not the most productive check you could do. But at the same time, if you build up this F statistic based on modeling assumptions, right, then the expected output of the F statistic should, for the observed data, should behave a certain way only if your modeling assumptions are correct. And then you would expect to see the same behavior in your posterior predictions if the model you've built is also consistent with those estimator modeling assumptions. If they agree, I guess there's one way of thinking about it here is you can look at these summary behaviors and you can try to interpret their absolute behaviors, right? What are the actual values of that summary? And then there's the relative behaviors where you're comparing the observed values and the posterior predicted values. Posterior predicted checks are mostly focused on that relative comparison, and that's why they're so safe and so robust. But the absolute value might be helpful and might help you kind of get a sense for how bad tension might be, I guess. if you have those modeling assumptions. So I don't know. Like I think it's. I guess in some sense, if the retrodirective check is kind of redundant because it's only like if it's true, like if your modeling assumptions are correct, it's going to be good. I don't know if I call that useless because it's still validating those model assumptions are correct, right? It's still showing not only are they correct, but they're consistent in the true data generating process in the model and the model that you're building. So it's still I still strain to think of that being useless there, right? I think the real problem to look out for is when you misinterpret retrodirective tension. And that just leads you down a path where you start adding stuff to your model that you don't actually need to add, or doesn't actually resolve the tension that you saw. So that can absolutely be a problem. You want to look out for that. But otherwise, I think it's hard. Like I wouldn't call anything useless necessarily. So long as you're stepping back and you're kind of separating the interpretation of the summary statistic from the construction and interpretation of the retrodirective check itself. Oh yeah, and so Michael's last comment here. So another thing to keep in mind is that it's often really helpful if you've read any of my stuff a while ago and you've in the meantime had a lot more chance to read other stuff, both my writing and other people's writing, and apply methods in practice, and you know you mature your own understanding of things, of what you know and what you don't know. It's often very helpful to go back and try rereading things. There might be a lot of stuff that you missed because you didn't have the context for, or you didn't really appreciate that was useful. So there's no shame at all in going back and rereading an old case study that you've already looked through, or a chapter, especially if you first tackled it when you were just getting started. Because there's gonna be a lot of stuff there that, in hindsight, you can kind of realize, oh, that's what I was missing here. This was missing here. This ties it all together. So that can also be really helpful to go back and reread things. And I often recommend people they'll ask it. They'll be like, I read this. I have these questions, and I get a sense for what they didn't really grasp in those initial chapters. And I'll be like, go back and read this section, and then it'll kind of click, and it'll help. But sometimes you need that, right? You just need to be exposed to something over and over again in different contexts at different times, and that can also be really productive. All right, another question from JD. Odds ratios for logistic models. Lots of arguments about log ratios versus relative risks and absolute risks. Oh boy, don't I know it. And that doesn't even take into account comparing all those things to linear probability models. Is there, I guess I'll summarize here by kind of okay, sorry. Let me get this comment from JD here, saying redundant is maybe what he was kind of getting at some of his questions. So one thing to keep in mind here, a lot of times these questions and answers, right? It's a discussion. It's a conversation. I don't necessarily fully understand the question. You might not understand the question. We might both not understand the answer. And the reason we have these back and forths in these conversations is to kind of iterate towards a common understanding. So hopefully through the back and forth, I've been able to kind of refine what I was talking about and offer something a little bit more towards what you were asking. And maybe you kind of better understood the kind of vague apprehension you had. But one other a thing that might be useful here is to try to come up with an explicit example with code and simulated data that demonstrates a problem that you're worried about. Right, so the F statistic that we've talked about here, code it up, simulate data from it, and then have a model that you can tweak so that there's some kind of model inadequacy, and maybe it's a model inadequacy that you think should show up in the ANOVA statistic and the F statistic, and there's an inadequacy that maybe won't show up. So, for example, like if your observational model, if the true data generating process is kind of heavy-tailed, and the model is not, then that might not show up in the F statistic. And do the test, see if it does show up, see how it manifests, if it manifests at all. And that can help you kind of work through, formalize a concern you might have had to the point where you can now ask that formal question, that precise question. Or it might help you realize that, what you thought was a circularity was never really circular in the first place, right? So these conversations are very helpful for that, both here on the Discord, etc. And to complement, I would definitely recommend trying to come up with kind of simulation studies to get at and demonstrate something you're worried about. And if you can't demonstrate it, maybe it's not something to be worried about. If you can demonstrate it, or if you can get some kind of weird behavior that maybe is taking a different direction, that might help identify that what you're worried about is something we're worried about, but in a different way than you initially thought. So yeah, keep asking the questions, keep having the conversation. It's all really helpful. And just as a complement to that, I think playing around with some simulation studies can also be really helpful for kind of one's internal understanding of things. All right, let's get to your other question here. Odds ratios. Is there a use for odds ratios from a Bayesian modeling perspective, or dare I say a generative modeling perspective? So I talk about this a bit, speaking about going back to old chapters. In my general Taylor modeling chapters, this is kind of my generalized linear model chapter. So what's cool about the odds ratio is that it's a little bit easier to interpret than a logistic function. And so let me kind of explain what I mean by that. So let's look at what happens when we have a positive function we want to model. Why don't we just use a Taylor approximation? Well, the problem with the Taylor approximation is that it's a good linear model around in some neighborhood, and that can approximate some kind of complicated nonlinear behavior. But when we try to approximate the behavior of a function that has constraints on it, it has a minimum and a maximum, for example, then that linear approximation becomes more difficult. If we're trying to approximate this function away from the boundaries, away from the constraints, we can still get away with a Taylor approximation. But if we need that approximation to expand out far enough that we're starting to get close to the boundaries, it's very easy for that Taylor approximation to violate our constraints. And it's one thing to have a Taylor approximation that's kind of inaccurate. It's another thing to have ill-defined values or improper values. Because then when you plug in those improper values to, say, a density function, it's not just that you're getting a small error, your code fails, right? You try to plug in a negative intensity to a Poisson model, that's going to cause all kinds of computational chaos. Bad. And there's some other kind of perspectives about the kind of fragility of doing just Taylor approximations or linear models in the presence of constraints in terms of kind of different length scales and kind of the size of the neighborhoods that you need or kind of the size of neighborhoods you can get away with will vary very strongly depending upon where you are in the space, and can be really careful with your base point neighborhood. It just gets very kind of tricky. So one way of robustifying yourself to that is to not try to model or approximate the constrained function directly, but rather unconstrain it, approximate the unconstrained function, and then apply the constraint again. And we do that with something called the link function. So a link function takes some constrained space and maps it to the real line. That way, when we compose our function of interest, or constrained function, that maps into a constrained subset of the real line, and then we compose it with this link function g, we get a function that goes from our input space to the real line, completely unconstrained. So now we can approximate this composite function without having to worry about constraints. This is a much easier Taylor approximation problem. Then at the end, we want to be able to think about those constrained function outputs. We can take our function we can think about as itself composed of the identity function. which is just the definition of the identity function. But the identity function is also the inverse link function times the link function. And we can just refactor this into this form here, right? So we can always recover the constrained function by unconstraining it and then constraining it again. But we can now use this same trick with our Taylor approximation. Instead of applying the inverse link function to the true composite function, the exact composite function, we apply the Taylor approximation, or apply the inverse link function to our Taylor approximation. And that gives us this very robust model where we're always guaranteed to satisfy the constraints, and we can be a little bit sloppier about things like the baseline point in the neighborhood and things like that. So this is one way of interpreting general linear models or generalized linear models. The fact that like people have different interpretations of those in themselves is the whole thing, but it's a way of kind of like thinking about this construction a little bit more in terms of kind of function approximation, which I think is a lot easier in most applications. Now, how would this work in practice? So let's say we have a positive function. So let's say like the intensity of a Poisson model or a negative binomial model. That's always a classic example. So the intensity function we're trying to approximate is constrained to be positive. It can only have positive outputs, no negatives. And a link function that gets rid of that positivity constraint is the log function. So we compose that intensity function with the log function. We're going to get a function that maps into unconstrained outputs. We can then approximate that composite function with the Taylor approximation. And then we impose the inverse of the log function, which is the exponentials. So we're going to take some kind of, say, polynomial model, hit it with an exponential, and we're always guaranteed to have positive outputs. Now, the nice thing about the exponential function is that it maps kind of these additive contributions that we get with a polynomial, that we get with a Taylor approximation model, into multiplicative perturbations. And this is really nice because it allows us to reason about all of these different contributions. So we have some baseline value, and that gives us our baseline value on the constraint scale. And then we have these additive corrections to that value, and those turn into multiplicative corrections on the constraint space. And so we can think about our, the constraint space, the actual physical space. We have this initial value, and then we're going to either multiplicatively increase it or decrease it, proportionally increase or decrease it, depending upon these additional corrections. And based on how much things can proportionally change, that allows us to get a sense for kind of bounding how large these terms can be, but can almost bound how long these terms can be. This gives us a really powerful way of building a prior model over all of these Taylor approximation parameters. Otherwise, we'd be dealing with kind of like a guess and check problem, where we kind of guess a prior for these parameters, apply an exponential to their combination, and see if what we get is reasonable. And that's always a handy thing to do, just to make sure that we haven't done anything bad. But it can be a little bit frustrating if we don't know where to start. So the fact that this exponential model not only gives us positive outputs, but also kind of preserves a certain algebraic structure. It maps these addition operations to multiplication operations, makes it really interpretable and easy to work with. And I have an example here in the chapter of how to do that. And one cool thing about this is even when you start thinking about proportions, even a relatively large proportion ends up turning into very, very small values on the log scale. And so when you think of like what are very conservative priors, end up being very, very strong priors numerically compared to like the normal 0.1, normal 0.10, normal 0.100 you might default to if you're not being careful. And then here's just kind of a diagram of kind of looking at these additive corrections and how they change the exponential output to make sure that things are still kind of staying contained to well-behaved values. Now, when we have an interval constraint, like for example, when we have a probability parameter that we want to model as the output of some function, the procedure is relatively similar. We have a logit function, which maps an interval to a real line. And then when we construct our approximation on an unconstrained space, we have to map it back to the to the interval, which we do with the inverse of the logit function, which is the logistic. So in a logistic regression, right, we're taking some polynomial model, which is our Taylor approximation on the unconstrained space, or plugging it into this logistic function, which then constrains things down to a interval output. And this is the classic way of modeling probabilities in all kinds of applications, a lot of medical applications, as JD mentioned. So what's the problem with this? So mechanically, it's very similar. But interpretationally, we're kind of boned by the fact that there's not really a nice algebraic conservation here. Right? Ideally, what we would have is these addition of all of these terms on the unconstrained scale would map into some kind of nice operation on the constrained scale. So we can think about logistic alpha as like our baseline probability, and we have some kind of operation that we can apply that then modifies that baseline probability while still keeping it in that 0-1 interval. Now, truth be told, there is in fact an operation that does this. And I'll come back to this in a little bit. But it's a weird operation. I promise you, I promise most of you, you have no idea what it is, and it's not going to be something intuitive that you can reason about. And that's where odds come in. So the odds function, we can think about as, say, a probability over 1 minus that probability. And it's called the odds because you're basically... The probability of success, right, is proportional to the number of successes that you get in expectation. 1 minus the probability of success is the probability of failure. And the probability of failure is proportional to the number of failures that you get. So you can think about the odds, at least in expectation, as the number of successes over number of failures, right? And those are the classic betting odds, right? When you have like 3 to 4 odds, you're expecting 3 successes for every 4 failures. For some reason, I think for some people who are familiar with gambling or have some experience with gambling, this kind of gambling interpretation alone is enough to make odds useful. Otherwise, we have to kind of train ourselves to thinking about what the odds means, and so we can interpret it appropriately. Another way of thinking about it, if we just take this equation here and multiply through by expected number of failures, it's basically a slope, right? And this is a nice diagram here where we can kind of think about a flat slope, right? Is when we get no successes, no matter how many failures that we have. And that's where the odds, the slope is 0, and the probability is 0. The probability of success is 0. We're never going to get a success. All we're going to get are failures. Whereas when we have an odds ratio of 1, we get the same number of successes and failures. That's probability 1/2, right? And that's a slope of 1. And so there's a nice kind of geometric picture here, where you kind of think about this kind of monotonic relation between probabilities and odds ratios, just different scaling of the values. But the real benefit of the odds ratio is that we can write the logistic function as a ratio of the odds ratio to 1 over the odds ratio. And if we kind of play around with our logistic model, that means that the odds ratio, if we're saying that our probability is the logistic of some polynomial approximation model, then the odds ratio is the exponential of that polynomial. And we just saw exponentials are really nice because they map additions into multiplications. And so the real power, the real benefit of the odds ratio is that we can think about them multiplicatively. If I have a model that's built up on a transformation of a bunch of additive contributions, the additive contributions themselves might not be immediately interpretable. And I can't really think about the logistic of all those additive contributions because logistics are really hard to reason about. But the odds ratio of those additive contributions turns into the product of a bunch of odds ratios. And so this allows us to think about our model here, all the individual terms in our Taylor approximation, in this polynomial model, in terms of a baseline odds ratio and these proportional changes to that odds ratio. So if I add a linear term to a constant, I can think about that linear term as proportionally scaling the baseline odds ratio. And if I add a quadratic term, that adds another proportional scaling of the baseline and that linear variation. And so this gives us something we can potentially reason about, right? If we can interpret odds ratios appropriately, which requires a little bit of training, and again, either think about the kind of gambling applications or thinking about a kind of geometric picture like this, can be really helpful. Of course, I have to do the Star Wars odds example, just because. If the subtitles in this chapter weren't enough of a nerd snipe, I got to put some Star Wars in as well. If we can interpret odds ratios relatively well enough, and instead of thinking about what's the baseline probability and how does that probability change, if we can think about what's the baseline odds ratio and how the odds ratio changes, then we can interpret all these individual terms, and we can translate them pretty immediately into constraints on alpha and all of these additive changes, all of these additive contributions, the slopes, the linear terms, the quadratic terms, etc., in our Taylor approximation. And that's huge. So the reason why odds ratios can be really useful is that with a little bit of training, to make sure you interpret them appropriately, then they allow you to think about all of these individual terms in your Taylor approximation, which then allows you to build principal priors for all those individual terms. And I think this is where the real benefit lies. Now, a lot of people don't interpret odds ratios correctly. And so if that's true, then none of this is going to be useful. I think it's absolutely true that probabilities are more interpretable than odds ratios, but changes in odd ratios are more interpretable than changes in probabilities. That's probably the right way of saying it. So when people talk about things like odds ratio, so that's from the modeling perspective, why odds ratios are useful. A lot of the arguments that people get into about odds ratios versus relative risks versus absolute risks, I think that's oftentimes those arguments are confounding a lot of different things. Some of it includes things like this, where there's a nice mathematical benefit to odds ratios. There's a nicer mathematical structure than, or a simpler mathematical structure than probabilities. But when you talk about like odds ratios versus relative risks, and then relative risk versus absolute risk, that gets into kind of two things, I think. One is connecting to the actual application of interest. And so, like absolute versus relative risk versus odds ratio into like, what's the best interpretation for people? What's going to change people's habits and things like that. And like, when we talk about like eating a slice of bacon has this huge, significant effect on health, but it's like a super tiny absolute risk. It's just a large relative risk because the risk of, dying of heart disease at a relatively young age is somewhat low, right? Or like these kind of like people get really on the policy side of things, people can be misled where they want to put interventions to minimize relative risks when it's really the absolute risks that matter, right? But that's policy, that's application, that's not building your model or interpreting your model necessarily. That can all happen after the fact, right? And you can build a logistic regression model in SAN, build do all your Bayesian inferences, and then you can translate your inferred probabilities to odds ratios, relative risk, absolute risk after the fact, right? So all that stuff is still useful, just not relevant to the model building. But the third thing I think happens is I think people, what happens a lot implicitly is that people will end up either trying to linearize probabilities or linearize odds ratios or linearize relative risks and absolute risks, right? And so you get 4 different kinds of models because you're not, like, these are all non-linearly related things, and people will then linearize different parts of it and then say that they're kind of complain that the results they get are inconsistent with the results that someone else got because, yeah, they're taking different linear approximations. It's not supposed to make sense when you do it that way. You take your approximation and then you translate things non-linearly, and then you'll get something that agrees with what happens in those other representations. But so often, especially on the medical side of things, people can only think linearly. It's all they want to think about. That's why people do linear probability models, even though they suck and they very rarely work. Some people are just convinced themselves they can only ever reason about linear behaviors. And so it has to be linear. And so the question is, well, what do you make linear? So if linear probability models are bad because they violate the constraints so easily, well, maybe a linear odds ratio model is better. Or maybe a linear relative risk model is better. But it's all all of those kind of arguments are trying to run away from nonlinearities and trying to find, what we're really arguing about is what is the best way to ignore nonlinearities? What's the most robust way? And that's definitely going to be application specific. It's going to depend upon what the true behavior is and all kinds of details, which gets into, the right approximation, the most robust approximation is going to depend on the context of the application. So there's no universal answer, and everyone arguing about there being a universal answer is talking past each other, and that's why it's such a garbage discourse. But if we ignore all of that and just focus on the probabilistic modeling side of things, odds ratios, absolute risks, relative risks, all probabilities, all have useful. They're all nonlinear related to each other, and they have useful but distinct interpretations. So we want to be able to take advantage of the fact we can map between them to map to the one that has the right interpretation at any given time. When we're building our prior model, might be nice to map to odds ratios, just to kind of get this multiplicative, proportional perturbation kind of perspective to help build our prior model for these alpha terms. Then we have that prior model, we can plug it into a logistic, get our probabilities, and interpret those directly. Or we take those probabilities, convert them to relative risks to absolute risks, and then interpret those. So it's a classic example where you have these different representations of a system. The maps between those different representations are complicated, but if you invest the time to understand them, then that allows you to map into whatever representation is most useful at any given time, and then map back or map to another one that's most useful at another time. And so, yeah, odds ratios definitely have a use in prior modeling. I wouldn't build my model directly in terms of odds ratios. It's more for kind of building the prior for these Taylor approximation parameters, then going to logistic regression. And at the end, depending upon the audience for the analysis, maybe going to another representation set of probabilities. And then I'll finally note here, just I won't go into too much detail because we're already going super long here. But if you are interested in what is that operation that you can take 2 probabilities and plug them into this binary operation and get another probability between 0 and 1, that we can kind of think about, a logistic of alpha plus delta alpha is logistic of alpha, some kind of operation, logistic of delta alpha. I talk about it here in this appendix. And so formally what we're looking for here are algebraic homomorphisms. What is the algebraic homomorphism that maps addition onto some kind of probability algebra? And I won't go into too much detail, but I'll just say there is it turns out there's actually quite a bit. There's a bunch of algebraic operations that you can define based on how you want to define your interval. Is it 0, 1, 1 minus 1, etc. So you can build it up generally. And it turns out that this operation is related to hyperbolic geometry, because it's basically what happens when you move along a hyperbola. You kind of think about like locally, you're adding kind of steps, but how you move along the hyperbola is nonlinear because the hyperbola is not straight. So kind of talk about how you can relate all of that to hyperbolic motion. And then what's really cool is that that operator does show up in places. It shows up in relativistic physics. It's basically how you add two relativistic velocities together. So I have two probabilities. I'm going to add them together so that they stay in 0, 1. Mathematically, it's the same problem as I have two velocities. I want to add them together so they stay below the speed of light. So there's a kind of a change in the interval boundaries, but once you account for that, it's the same thing. And what's cool about that is now you can start directly relating concepts in logistic regression to concepts in relativity. And this is very cool for me, who studied physics originally. So if you haven't read this chapter before, as I've thrown all these chapters up, if you haven't read them before, definitely take a look. If you have read them before, maybe take another look. And this one particularly is really cool. It's a fun party trick of being like, oh, you think in order to understand logistic regression, you have to understand relativity. Which means that if you take the work to understand logistic regression really well, you actually could know quite a bit about physics. But also give you a sense of like, it's okay to be frustrated with logistic regression. It is a freaking mess because it is literally the mathematics of special relativity. All right, so hopefully that addressed everything there, JD. Okay, 2 more questions. All right, so for those who I want to emphasize, for those who are kind of have stayed this far, if you're getting tired, if you need to drop off, definitely drop off. The VOD's going to be available immediately after we're done here. You can catch up after the fact. If you're watching this after the fact, definitely break it up. Take some time to get up and stretch and the like. Don't have to marathon this if you're getting tired. All right, so Yair's asking about how can we build a model that has probabilities and probability densities in the same model? His example being sometimes you get these continuous observations of this kind of underlying titer, this kind of concentration. And sometimes you get this kind of discretized or censored observation where you only know kind of ranges instead of the exact continuous value. What does it mean to kind of consistently build a model for those different kinds of data at the same time? So I wrote up just a few kind of notes here. Be a little sketchy, but hopefully this will kind of formalize things enough. So one thing to keep in mind is that we're talking about observational spaces. We're often talking about product spaces. Product spaces are built up of individual component spaces. So in the kind of mathematical notations, we write y1, xy2, xy3, et cetera, and you'll often see this notation here where the x here isn't the letter x, it's like the mathematical operation times. But it'll be like times, and then it'll have bounds on it to kind of indicate that you're repeating this product operation on these subspaces. So often we think about these component spaces as being homogeneous, like they're all the real line, or they're all integers, or they're all the positive real line, etc. But mathematically, there's no reason why they can't be heterogeneous, right? It's totally well defined to have an observational space where some of the components are real valued, and some of the component spaces are integers, or positive integers, or positive reals, or interval valued reals, or whatever it might be. Totally fine, right? And that means when we build up a probabilistic model, a probability distribution over this observational space, our representation of it isn't going to be homogeneous. The way we represent that probabilistic structure on the continuous components is going to be with probability densities, probability density functions. And the way we represent it on the say discrete components would be with probability mass functions or just the atomic probabilities. So, for example, kind of an example, kind of mimicking what you talked about there, Yer, is that on the continuous components, when you have a continuous observation or a complete observation, you might model it with a normal. There's some kind of latent location and some variation, and you're getting a sense, like all these continuous observations are kind of telling you something about that centrality and that dispersion. But when you get these censored observations, these discretized observations, you don't observe the continuous value. Instead, what you observe are a set of discrete values. In this case, say we have a set of finite values. So we get a categorical model. And that categorical model is defined by a set of probabilities. Now, those probabilities might say to be defined as an integral over the probability density function we're using on the other components. It doesn't have to be. It can be something completely unrelated. It could be related to, there's some kind of like your detector breaks, and when it breaks, its output is determined by a completely different thing. That's nothing to do with the system that you're trying to study. Or it could be that when it breaks, it gives you an incomplete observation. So you only get a sense of what window, what bin you fell into. The classic example of this is censoring, where you have some kind of detector and it has a minimum sensitivity. So if your observed value is above that sensitivity window, that kind of background, you can see it and you report that continuous value. But if it's below the background, the detector might not see anything and then just report, say, a 0 or an unobserved value. Say, like, something was supposed to happen here, but I couldn't see anything above the background. So I'm going to give you an NA or a 0 or some kind of like default code. In that case, the probability of that event, knowing that like something was supposed to occur but it didn't get reported as a continuous value, that's the probability of everything below that background level, which is another integral of the continuous model. So one way of thinking about this kind of heterogeneity, this is going to get a little technical, so if this is not something you're familiar with, don't worry about it. But remember that probability distributions, probability density functions, and probability mass functions are different things. A probability distribution is an absolute object that defines probabilities and expectation values. Probability density functions, probability mass functions are representations of that distribution that rely on other structure. So a probability density function can be used to calculate probabilities and expectation values in the context of a reference measure. Probability mass functions can be used to construct probabilities or compute probabilities and expectation values in the context of the counting measure, right? Where we sum things. Whereas a probability density function over a real line is defined in terms of the Lebesgue measure, which allows us to integrate things. So when we talk about these density function representations, they're relative to a reference measure. And when we have heterogeneous component spaces, the natural reference measure on the product space is going to be this kind of weird amalgamation of amalgamation of, say, Lebesgue reference measures on the continuous components, and then counting reference measures on the integer components, or the finite components, or whatever components you might have. So formally, what you're doing when you have this combination of density functions and categorical probabilities or probability mass functions, however you want to interpret it, what you're really doing is you have this joint probability distribution defined over the product space. You have this heterogeneous reference measure that's built up of Lebesgue measures and counting measures. And then when you construct the Radon-Nikodym derivative of your probability distribution relative to this heterogeneous reference measure, you get this kind of like odd product of density functions and probability mass functions or categorical probabilities or whatever it might be. And that's totally okay. It's totally fine, right? You're not defining a standard program isn't specifying a single probability density function, where everything has to be continuous. It's defining formally a product rate of Nyquist derivative that can be built up from probability density functions over continuous component parameters, if you will, and then these discrete structures, categorical probabilities or probability mass functions over the discrete parameters. And that is totally fine and totally well behaved. So it just helps. Sometimes I think when we can get a little bit lost when we're just used to seeing examples where it's like all density functions or it's all probability mass functions, and it's not clear how to kind of combine them together. It can help sometimes to back up and just think about, okay, what is the actual product space? What are the reference measures on those product spaces? And then kind of rebuild back up to that joint density, that joint rate of Nyquist derivative that includes both continuous density functions and these discrete probability mass functions. And then I've also just mentioned here briefly another way of kind of constructing these systems where you have sensoring, where there's kind of this like switching in the output of the data generating process, is to consider augmenting your observational space with a 0-1 indicator. So you add this binary variable to every component observational space that indicates whether or not it's a complete observation or an incomplete observation, or a censored observation, for example. So now what you can do is say, like, the yn would always be continuous. Well, sorry, no. I don't want to say this. Okay, so there's a few ways of constructing this. So you can construct it where the yns are still heterogeneous, and then this binary variable, which I've labeled 0 here, will just tell you which one it is. It just adds additional like labeling to help organize what's going on. The other way of doing this is that you can take a product space like this, and then damn it. All right. You take a product space like this, and then you have the yn, all the real line. And then you consider like a projection function that goes from yn to some kind of, I don't know, it's called xn, right? And then the output of this space can depend on this variable here. So this can be helpful where it's like, what you're really modeling is like your component observational space is xn, this kind of projection, and then the behavior of that projection depends on this kind of switch. And this is sometimes a little bit easier to work with mathematically, not to implement the model necessarily, but to derive the model. This is where, for example, you can like derive selection models and figure out why you need to condition on certain things and why you get that like weird integral normalization. But I just want to mention that because there are ways of trying to like derive that heterogeneity instead of starting with that heterogeneity. So you can always kind of like step back, start with a homogeneous system, and then you have some kind of mapping that's introduces that heterogeneity instead of just starting with a product space that's heterogeneous from the beginning. But that's much more useful on like the technical side of things, where you're deriving these like subtle calculations. And like if you're just building your model, just recognize that you're building a product space, a model over product space. If the component variables of that product space are heterogeneous and some are continuous and some are discrete, not at all a problem. That you're going to have some probability densities and some probability mass functions. And the beauty of the standard modeling language is that you can just write those continuous density functions, and discrete probability mass functions, or discrete categorical probabilities anywhere you want, right? It all kind of merges together into a single joint model evaluation, and that's all that matters. So hopefully that answered that question. If there are other, if it didn't, or if you want to follow up on anything, just throw a question up on the Patreon, and I'll try to address it in the near future. I'm just realizing all right, so I don't do this often enough to have like a good routine. I should have started the whole thing by mentioning, thanking all my Patreon supporters who make stuff like this possible. You also get early access to a lot of the stuff that I've showed you here so far. And then also mention that I'm teaching the remote courses starting next week, covering advanced Bayesian modeling techniques for mixture modeling, survival modeling, pairwise comparison modeling, which is things like item response theory, Bradley-Terry modeling, and then finally ordinal modeling, where you're modeling ordered ordered outcomes, ranks, if you will. Yeah, and there's still time to register for those courses. It's a little late now, so only the most dedicated people are going to see those ads. But if you know anyone who has the time and might be interested, definitely spread the word so they don't miss it. Because I probably won't teach this stuff again next year, if I'll even teach again next year. The registration numbers keep dwindling to the point where it's becoming less and less cost effective to teach it all. So yeah, get in on it if you're interested. All right, so with that said, let's get to the last question here. So this is from Stanley, some very kind words, and is joining a medical stats master's, kind of tying in a little bit to that first question from Spencer. And Stanley's asking about particular texts that I'd recommend about kind of learning about principled modeling and modeling a data generating process and this kind of neurogenerative approach that I recommend so often. And this is another question I've answered a few times in previous office hours and various forums. So the problem is that I don't think there's a good reference for any of this. And that's not to say that the things that I'm doing and writing about are novel. It's just that they are fragmented historically. So statistics, academic statistics, where most of the textbooks come from, have historically been focused on math and kind of example applications that don't have anywhere near the complexity of a real application. In applied fields, in the sciences, for example, where you need this really where like there's a clear data generating process, and you have the context to think about modeling assumptions and prior modeling and things like that. There is there's often not the mathematical formalism and probabilistic understanding to do statistics in any kind of self-consistent way. So you get these heuristic methods that then, not only is there the distance because academic statistics doesn't really care about applications, but you look at this further distance in the sense that what the applied fields develop is heuristic and arguably inconsistent. So then, when you try to then connect those people, there's a lot of disagreements, and it doesn't really kind of flesh out, right? So there's this gap in the middle between applied statistics or between applications and sciences and even a lot of industries and academic statistics. And there have been, over the decades, lots of people who try to fill in that gap a little bit. But it's not so much that they start right in the gap and then try to reach out in both directions. They'll kind of make small steps in very particular ways. So they might show from a statistical perspective slightly more applied consideration. Or they might take a particular kind of applied work, applied analysis, and formalize it more statistically. So you end up getting are these pockets of really good and interesting work, but those pockets might not be directly applicable to what you're doing. Or it might not be written in a general enough way to even understand whether or not it's applicable to what you're doing. Or the statistical methodology might not be comprehensive enough. Like parts of it might be useful, but it might the whole like there's not enough of a procedure or workflow that you can apply wholesale. Or it might be older and not using the kind of modern computational tools available to you. So the challenge is that while there's a lot of incredibly cool insights and great writing historically, you have to go into it knowing the context of what each of those references might be missing or what's incomplete about it. So I'm trying to fill in a lot of those gaps and provide this very kind of complete, comprehensive picture. And I think that's what, if anything, is novel about my writing. I'm sure it's not reaching everyone, it's not perfect, etc. But that's what I'm trying to do, and I think it's one reason why it's certainly people here have appreciated it. And I'm drawing from a lot of these resources, but it's taken a lot of time to understand what to pull from them and what is antiquated or out of date or was limited by certain kind of tools. So I'll provide. I'm just going to talk about some of my favorites, but I also kind of want to briefly mention their limitations. So let's start in kind of, for me, temporal order. So when I was in grad school, I was doing my PhD in physics. I had taken some stats undergrad classes, nothing, it was all compelling. But I did a lot of data analysis. So I was an experimental physicist, so you learn a lot of kind of stuff on the job. In the lab, everyone has their own kind of heuristics for data analysis, and you learn those. And there are sometimes you'll get like data analysis classes and the like. But when I got to my PhD project proper, I had a good founding in this kind of heuristic physics data analysis techniques. But when the postdocs you're kind of assigned a project, and one of the postdocs was saying this project's gonna be really hard. It's going to require a lot of like careful statistics. You should use this machine learning thing that everyone's talking about. So this is like, oh wow, this is a long time ago. So this would have been like 2007, I think. So I was like, okay, well, and then he gave me like a handout for linear discriminant analysis, which is not even then really considered proper machine learning or a state-of-the-art tool. So I went to a colleague of mine and who had done neuroscience as an undergrad, and he was also in the same city as mine, as far as doing my grad school. And so we're hanging out, and I asked him, hey, like neuroscience, I know there's a lot of overlap with machine learning. Are there books you'd recommend? And he had done a semester abroad in Cambridge and took a class from David Mackay and the infamous information theory, inference, and learning algorithms book. So he recommended this book. And if you read through this book, I think it's chapter 3. Let's see. Yeah. So he begins chapter 3 with this example of a broken detector. And like, how do you handle this? And he's trying to motivate. He's like, oh, when I was an undergrad at Cambridge, I had this physics problem I had to analyze. I didn't understand it. And my advisor or this supervisor told me about this whole Bayesian modeling thing. And so he goes to proceed to kind of like show a quick, very simple, like one parameter analysis of this problem. And it hooked me immediately. It was like, oh my God, this is great. You're modeling the entire experimental process. Like this is perfect. This is what we're trying to do heuristically in physics and doing terribly at. Plus you have this like Bayesian probabilistic modeling thing where the inferences are kind of cool and like uncertainties being quantified as a first class object. This is freaking amazing. And then the rest of the book is almost nothing to do with that again. The book's great. Like, there's a lot of cool mathematical insights and fun puzzles, and there's a few spots here and there, but there's not really a coherent discussion of modeling. There's a lot of Bayes theorem. There's a lot of kind of machine learning methods, but there's not a kind of a discussion about how you model your own data. Now, the other book my friend recommended was Bishop, Pattern Recognition and Machine Learning. Now, this book is interesting because nominally there's nothing in here about probabilistic, like it's you wouldn't superficially, you wouldn't necessarily think there's anything about Bayes theorem or probabilistic modeling in here, and yet just about every example, it's kind of organized around here's a machine learning method, and here's how it works, here to do it right. And almost every one of those chapters is basically here's a machine learning method, here's how it's really a Bayesian probabilistic model, and then here's how we can use Bayes theorem to get inferences out of it. And so again, like you wouldn't read this necessarily looking for that, but if you happen to read it anyways, it's all of a sudden you're getting like, oh, okay, yeah, I like that information of Gaussian processes. Oh, okay, hit a Markov model. It's really just like this data generating process. These graphical models and these kind of message passing, you think about them as like flowing along the direction of the data generating process. In fact, I believe they mentioned data generating process multiple times in the book, right? So this and Mackay both kind of set the possibility of this, and then you can read all the other like Bayesian textbooks. I went through all of them, and they'll talk more about Bayes' theorem, but they never really talk about the modeling aspect. The model's always taken for granted. If the model's just like a thing that you get, don't worry about it. And so what ends up happening is people only learn black box models, and then they apply like Bayesian methods to them. And most of the time, all they're really doing is taking an existing model-based estimator and then using the prior as kind of a regularization, and then quoting a posterior mean instead of the estimator output, the raw estimator output, right? That's not really taking advantage of Bayes' theorem. That's not getting probabilistic predictions and generalizing and adapting the data generating process to changes that might happen in the future. Like it's not really getting to like the real power of this stuff because there's not a model that you can build and adapt. And that's where I think there's still a huge dearth of understanding. This is perhaps the biggest gap between applied analyses in academic statistics is the development of bespoke models appropriate to the context of a given application. And again, there's kind of exceptions here and there. Actually, let me grab one other book. So I'm currently working on my next chapter, which is going to be on discrete choice methods, which are big in econometrics, marketing, and the like. These I've known about for a long time. I've helped people kind of build some more general models using some stuff, in Stan and the like. But I haven't really like sat down and kind of dug through them in real detail enough to write a chapter. So the story I mentioned on the Patreon recently is I kind of decided I wanted to do this chapter next. And so I got a bunch of electronic resources. So I know a bunch of people who have done this before, so I know kind of where to start looking and then look at their bibliographies and what they recommend and collected some stuff. And one of the references I got to was this book by Train that was supposed to be pretty comprehensive. And then the next day, literally the next day, like I was doing this at 11 p.m. midnight. And then the next day I was hanging out with a colleague. We were getting dinner in the East Village of New York. And we walked by a bookstore, and my friend's like, "Hey, this is a fun bookstore. We should definitely check it out." And so we got some tacos, and then went to the bookstore on the way back. And this bookstore is tiny. It has literally 2 shelves like this big on math. And when you get like a math section in a used bookstore, it's a lot of like learn calculus, and then it'll be like weird stuff, intro stuff like that, and then it'll be like a weird selection of textbooks from whatever kind of lots they happen to have purchased. And in this case, the book one of the references I had kind of collated the night before was on that shelf. amongst a bunch of completely random stuff, right? Not in an economics section, not in a marketing section, in the math section. So it was kind of a sign. Anyways, so the book's pretty good. And one of the reasons why it's good is that it derives a lot of these discrete choice models as a data generating process. You have these competing alternatives with their own utilities, and the output of somebody's choice is going to be based on the alternative that is the highest utility. Now, those utilities have some variation to them, so you have to convolve that variation in, and that's how you get these discrete choice models, for these different models for how the utilities can vary. So it's great, right? Like there's like this immediate data generating process recognition, but they don't call it a data generating process. It's just the economics model. And then very quickly, you start getting the whole kind of like model building stops. Because to go any further, to add any more complexity, you need computational tools that aren't available to you. So you start getting these kind of partitioning of discrete choice models into different kinds of discrete choice models that are all based on these very kind of rigid set of assumptions, because each of those rigid set of assumptions corresponds to a classic algorithm that you can use. And you can't go any further because you don't have the tools to go any further, right? So they talk at the very, very end about like Gibbs sampling and Bayesian methods that allow you to kind of really generalize much further beyond what you might do, but Gibbs samplers are slow, right? It doesn't really allow you to go that far. So with HMC, we can completely obliterate those obstructions. And now we can think about this much more generally, as here's this general construction for choice models, this data generating process, and now there's all the bells and whistles to that data generating process. Nothing stopping us. In particular, for those who might know anything about economics and marketing, the incorporation of endogeneity, things like the BLP model, trivial to do from a generative modeling perspective. You just get two terms that depend on price, and you just add that to the joint model. Straightforward, done. Conjoint modeling, combining multiple surveys, all just completely straightforward. But because they don't have a tool as general as HMC, those kind of options aren't available. And so like as useful as like cool as this is as like you read it and you go, oh, that's a data generating process for this particular application. Very quickly, that perspective gets halted because of the computational tools that were available at the time this was written and that are popular in that field, right? And this is true in a lot of places. There's a lot of applied references where there'll be bits and pieces that are like so close to embracing this data generating perspective, and they get obstructed by saying like, oh, we can't fit that model, so we're going to fit this simpler one instead. Not recognizing that actually, yeah, we can fit that model. So part of the challenge here is that like to get a kind of a combine data generating modeling and probabilistic modeling and applying it in practice, you need these very general tools, and it's only with the advent of HMC that we can really push the boundaries and start talking about these things in a really comprehensive way. So that's just one example of like an applied reference that does really cool stuff, but is still kind of limited, and it wouldn't be a reference I'd recommend out of context, right? You have to kind of like know when they talk about like we only go this far, is that because you can't go any further, or they just haven't gone any further? And then two other references that I really like. The first is Good Thinking. So Good Thinking is a collection of I.J. Good's essays, papers, things like that. It's a Dover book, so it's like $15, and it's great. So I.J. Good is British. He worked at Bletchley Park under Turing. So he's been doing like crazy analyses for a long time. And for some reason, he doesn't get like ranked as like the top Bayesians, but this is applied Bayesian thinking. This is like the philosophy of doing Bayesian inference in practice. So things like prior modeling is never going to be perfect. What are the consequences of that? I've only ever seen good talk about this. Everyone else is like, your prior is your complete encapsulation of everything you know. What's so hard about that? How do you translate your implicit knowledge into some explicit bit of information infinitely with perfect generality, with perfect precision? You can't. Not in a finite amount of time with finite energy. Good talks about it. It's so good. So good. Yeah, so good. So good talks a lot about these kind of conceptual issues of prior modeling and limitations of observational models and approximate models, and when they're good and when they're not useful and things like that. But there's nothing systematic in here. There's nothing about how you build a model mathematically. It's nothing about how you validate a model or anything like that, or kind of how you fit a model. It's very conceptual, very philosophical. And it can be a little bit awkward to read if you're not prepared for Good's writing. He's very British and very dry in his humor. So it's hilarious once you realize he's joking most of the time. If you don't realize he's joking, it comes across as like really dry and almost boring. And then once you realize he's kind of making fun of you and himself at the same time the whole way, it becomes a lot more engaging. So, and again, it's cheap. I cannot recommend this one enough. And the other classic is Box and Tau. So a lot of Box's books have a lot of overlap to them. This is the most Bayesian of the books. I've got a bunch of the other books over there that will go into more like particular techniques. Some of them are presented more frequentist, but Box always kind of gets a little Bayesian jab in there. This one is manifestly Bayesian the whole way through. The cool thing about this book is that it was written in the 1970s. And, we're used to seeing things like conjugate Bayesian analyses. We're used to seeing a lot of things that people argue you have to do because it's your only option. Box does a 3-component order differential equation model analytically in the 1970s. No conjugacy, nothing. This is the kind of really compelling stuff, right? Like, this is like, everyone lies to you when you say you have to do these things for simplicity's sake. Box is like, no, you don't. Here's what you can actually do. So there's definitely compromises here, right? There's things like, there's no MCMC at this point, at least not in statistics. So there isn't, everything has to be done analytically. And there's a lot of compromises that have to be made to do that. But they do it in a really principled way. So for example, when they talk about uniform priors, they're not talking about priors that are uniform everywhere, which have terrible properties. They're talking about priors that are uniform in the neighborhood of the likelihood function. In other words, they build up these posterior density functions from a likelihood function and basically a flat prior density. Not because they think the prior is flat everywhere, but because they think the prior is flat in the neighborhood of the likelihood function. Now, what's the consequence of that? It means that you have to go back and verify your likelihood function is actually pretty narrow. And they do. They explicitly check it. So they mention that like the flat prior models they use are an approximation, and they can validate that approximation, and they actually do validate that approximation. It's wild. It's so good. It's so much better than every other Bayesian textbook out there, despite the fact that it was written in the 1970s. That said, if you want to take these ideas and you want to apply them to modern techniques, it's not going to be sufficient because we have better tools. We have probabilistic programming. We have Hamiltonian Monte Carlo. We can build and fit much larger models than we could in the past. So a lot of this stuff, the kind of exact procedures are somewhat inadequate or somewhat out of date. But the conceptual stuff, the validating model assumptions, the visual checking of models, the consideration of units, and it's so good. But you have to have that context that this was written at a time before the tools that we have now were available. But I absolutely still recommend it. It's so refreshing to read this after reading books like Bernardo and Smith and Bayesian data analysis, even like McElrath. It's just like it hits everything, and it's just not where we are now. If anything, I think my writing, what I'm striving to do, is combine good and Box with our modern computational tools. That's really all I'm trying to do. And all of the stuff that flows out of that, all of the individual modeling techniques and the workflows and things like that are all just consequences of combining those with better tooling. There's not that much novelty out of that, right? It's just combining those things that haven't been combined yet. The other, so as I mentioned, a lot of Box's stuff is a little bit redundant in that if you read like the intro chapters of this book, it'll be the same intro chapters in like statistics for experimenters and the response curve book and things like that. So this is the one I would recommend over the others, just because it's the most kind of compact. But you're welcome to read the others, and just keep in mind that there's going to be some kind of commonality. One of the things that you do get a lot is Box's kind of perspective on statistics and the scientific method as being kind of the same thing. In other words, the implementation of the scientific method, if you really want to do it formally in a quantitative way, you need statistics. There's no way around it. And so he talks about this here, and this gets into the scientific method is about iteratively building models. So that means your statistical models can be iteratively developed, and he kind of combines it together into a really consistent framework. And he has a bunch of kind of classic diagrams for this. There's also an individual paper called On Science and Statistics from Box. I think it was the 80s it was put out, but it's basically what's in like the intro chapters to all of his books. And that's another thing I'd recommend taking a look at. Again, it's not going to tell you how to build models in particular or fit them using modern tools, but it does kind of really lay down that philosophical foundation and the limitations of what we can do in practice. We're never going to build our perfect model initially. We have to iteratively develop our models. That's just a fundamental limitation of the scientific method. So I'd highly recommend taking a look at that as well. And this is where Box's "all models are wrong, but some are useful" quote comes from. It's when he's talking about the scientific method and statistics. So you can get the quotes here. It's in most of his other books as well. He repeats it over and over again. It's also in the statistics science whatever it's called, the science and statistics chapter. In fact, I have a. So let me go here. Let me go to. Oops. The Patreon, and if you search scientific method, you should get, on this chapter, this post here on the implementation of science. This is another public post, so anybody can view this. You can recommend this to all your friends. Oh no, sorry, not this one. Where is it? I do a live stream. Yeah, here it is. So I was at a workshop in early 2024, and I decided to give my talk on this idea that how do we implement the scientific method? We need statistics. All the stuff that we talk about with like iterative model development and all of these ideas are just ways of implementing the scientific method. And then I did a live stream of that talk as well. So for anyone who wants to see it, so it's here. Just search scientific method on the Patreon and scroll down. This is public. And you can see the slides, and there's also a PDF version of the slides as well. So there's all these kind of figures showing the scientific method, and then plugging statistics in there, and how it's all integrated and wonderful. And it really all comes from Box's philosophy, but just in a little bit more contemporary perspective. So those are some references. They're all in some way incomplete. I'm sure my writing will be incomplete as well, if not in the future. If not now, then in the future. But the challenge here is kind of going into something knowing it's going to be incomplete, and ideally you would have somebody to tell you why something is incomplete, and that's going to depend a little bit on where you're coming from and what you want to learn about. And a skill that you can really develop is when you're reading something, getting a sense for when is this aligned with how I want to approach something, and when is it deviating. So when it's deviating, you can get a sense for, okay, maybe I've exhausted the utility from this reference now. Maybe I want to move on to something else. You can learn and appreciate what they're doing that's different, but also not be mistaken to thinking that you have to do it that way as well. To really, isolate, when are they thinking about data-driven processes? When are they modeling things explicitly? What can I learn from that? When are they doing Bayesian inference in a way that I think is useful and productive, etc.? And that'll come with time. So I'll definitely take a look at those with those caveats. But also, just keep in mind that when you're trying to learn about these really sophisticated topics, these really broad topics, nothing's going to be completely aligned with how you will eventually approach things. So keep that in mind. It's not that they're wrong; it's just that they're taking a different perspective, and kind of try to develop that skill of looking out for what's consistent with what you want to do, what reinforces what you want to do, what facilitates what you want to do, and when is it starting to deviate away from that. So you're not, kind of misled down a path that ends up being unproductive. And that's a skill you'll just develop. It doesn't take too long. Pretty quickly you can start getting a sense for, okay, cool, I can see now they're going down this direction because they're wanting to just build algorithms and not really think about models anymore. Cool. And if you want to follow that path and learn about it, awesome. But you're not going to kind of be misled into thinking that that's how every Bayesian analysis has to go. All right, so I know there's been a bunch of questions here, but I haven't been able to see them on the OBS. Let me get here. Professor Quintuple Fives. I have a colleague who was just last week telling me problems he had with big BLP models, inflation R package. Yeah, great. So at some point in the near future, I will have this chapter out. It might take a while. There's some subtle things that I'm still trying to wrap my head around in the presentation. I'm at like 25 pages of notes in integrals, and there's just a lot of tricky things where I want to make sure that I'm not misstating things. So a lot of times you have to kind of rederive it from a purely probabilistic modeling perspective to make sure that you're saying things fairly. And then the BLP model is tricky because it's literally like you add one term to a Gumbel discrete choice model, or what's also called a logic discrete choice model. And it's literally just like, having price influence two parameters at the same time, which is trivial from probabilistic modeling perspective, but not possible using the kind of standard tools in discrete choice modeling. So that's another thing that I'm hopefully going to kind of mention. A long time ago, I was helping an economist out, and they're specifically talking about this BLP model. And they were like, but there's these two things that both depend on price, and there's no way to handle them at the same time. And I just like drew the price circle, and I drew arrows to the two things, and I'm like, there's your model. And this person was like, what? You can't do that. I'm like, yeah, I can. Like, what? And then they, like, within a day, they had written it up and had sand code and an example, and it was working, and had a kind of a nice write-up of it, which I think they took down. I can't find it anymore. But yeah, it is really sometimes that simple. It's just needing the right perspective. Yeah, so there's if you're trying to like kind of convince people that these ideas are useful, as you were talking about earlier, it's less about trying to be combative and more about kind of giving them opportunities to read stuff. So I don't, and it's going to be about tailoring the material to what's already resonant with them. So if the die rolling or Netflix case studies might be kind of impactful, definitely give that a shot and see if it kind of hits them. There is some commonality in the die rolling case study with discrete choice models. It's not necessarily data generative, but the mathematical structure of the multi-logic models that I use at some points in the die rolling case study is basically the same model to use in a lot of discrete choice models. So that's one of those things where like they might read through that and go like, oh, I've seen that mathematical model before. How would that connect, etc. But might also need to wait for the discrete choice model chapter. Although I should warn everyone, I don't know if the discrete choice model is going to be public. It's definitely going to be available to Patreon supporters. I may be offering this one for cost. So we'll see how this goes. This is going to be kind of an experiment. But I've got to write it first, and then I'll decide what to do there. Yeah, if your colleague is like, definitely coming from that kind of econometrics perspective, where it's like, here's our 5 models, and we only do these 5 models, and we don't ask any questions about why we do anything else. Having that discrete choice application chapter might be the thing that goes like, okay, cool. We can go further, and that might bring them in, right? So it's about like, again, that exposure, exposing people with the right kind of stuff to just start getting to ask questions and think about things, and that's what really kind of brings them in. So again, that kind of ties back to that question about the causal inference stuff. Like, you're not going to argue with people and succeed. However, there's a lot of people out there who are frustrated by causal inference methods, and if you can provide, especially in your field in particular, if you can put something together that that kind of like demonstrates some of the issues and some other ways of tackling these problems that is specific, is kind of a case study in your field, that can go a long way towards bringing more people in. So I strongly recommend, if you're an applied field, and even if you don't necessarily understand a lot of the math, or you feel like, whether it's imposter syndrome, or you don't feel up to like doing something really detailed, try a case study. I cannot recommend this enough. It gives you an opportunity where you're forced to really dig into something. And if there's bits and pieces that are inconsistent, then you'll see that inconsistency in the writing. And that might convince you to go back and dig a little bit deeper. So you learn so much putting these things together. And then you have this new document that can target a whole new audience that I can't target, or I haven't targeted yet, because I'm not familiar with that application or that field. So definitely, if you think these ideas are useful and you want to kind of spread them, one of the most powerful things you can do, besides recommending the material to people, is to come up with these case studies to try to help translate and bridge the gap between these more general methods that I tend to write about, and then kind of their particular applications in certain fields. And then if you get people to sign up to the Patreon, high fives to you. I never. I'm only out in the real world every now and then when I get invited to stuff. But if you ever find me in person and you've supported me on the Patreon, or you have convinced someone else to join the Patreon, don't. I always carry these dice with me, my kind of warps dice. Oh. So don't hesitate to walk up and ask for, say like, hey, I've supported you in the past. If you supported in the past for any amount of time, whatever financially you've been able to do, if you've been able to support it all or recommend me to other people, let me know, get a die, and have some fun at your next board game event. All right, last question here. Jay was mentioning all the good one-liners and good thinking. Yeah, it's so like, you might notice all of the kind of sticky notes here. These are all basically one-liners. And some of them are like, they're not necessarily funny out of context. But I don't know. Like, if you're into stats and you've been frustrated with stuff before, some of the stuff is just like acerbic and biting, and just like, you're either like laughing out loud, or just like, you want to like, give a little fist bump or a high five or something. So good. It's such British, like, just assholery comments, but like, you don't notice it because it's written in this like British, kind of almost bland language. It's amazing. Highly recommend taking a look. All right, last comment here. Yeah, thanks, JD. Again, I think my goal here is really trying to bridge that gap between a lot of the academic statistics and theory to applied work, and not start at the applied work and make little infinitesimal steps towards theory, not start at theory, make little infinitesimal steps towards applied work, but really start in the middle and build out until there's this really clear bridge and we know how to walk back and forth. And then what's cool about that is some people can walk back and forth, right, and live in both those roles. That's awesome. But a lot of people don't have to. Once you have that bridge, people can decide how far they want to go. So because the bridge is there, if somebody just wants to understand how to use MCMC more robustly, they can walk a little bit down that path. And if they want to consider developing their own algorithms or critiquing new algorithms that their colleagues may have developed, they can walk further down that path. The point is the bridge is available to them, to anyone, and they can go as far as they need to. And that's the real dream. And so the only challenge with that is that it's not really a one-dimensional bridge, right? Everyone on the applied side is coming somewhere a little bit differently. So really, what the hard part is, there's going to be like 1,000 bridges coming in, the general techniques in theory, and then taking that theory more and more formal to all the way to the kind of academic side of things. So I've really started with the kind of like conceptual and general techniques in the middle that you can apply to any field. But and then as much as I can, I try to write about applications in particular fields. But I'm always going to be limited by that. So I cannot encourage people enough to give a try writing a little case study up in a field you're familiar with. If you're writing up a paper and the methodology section has to be like 3 sentences and you can't really talk about any stuff that you've done, do a preprint or a website, chat, blog post, or case study where you go through all those gory details. Right? A lot of people want to know that stuff, and that's what's most engaging and exciting. And as I mentioned before, not only does your putting it out there give that stepping stone to everyone else, but you learn so much in the process of doing that. So it's not just for the benefit of others; it's really for the benefit of yourself. And cannot recommend it enough. It's work, it's tough, and it's frustrating, and it's hard, right? But it's definitely worthwhile. And I think it going back to the first question Spencer was asking about, how do you learn this stuff better? How do you develop better tooling on your own when you don't have a cohort to work with and things like that? And having a particular project to work on, and these case studies are exactly those kind of projects, can be really useful for that. Because you want to make sure that kind of everything from front to back is self-consistent and self-contained. And if you see holes where you're making some kind of weird jump, you want to fill that hole in. And that requires you to spend a few days learning about something new. Awesome. You've learned more. You have this more comprehensive picture that you can provide to others. Everyone wins. So yeah, don't, I'm writing as fast as I can, but don't rely on me to write about everything. The more voices we have out there, the better. The more presentations as material we have, the better. The more it kind of expands the community that we can grow, which then just makes these tools more available and hopefully makes science a little bit less terrible. So definitely feel free to get engaged out there. If you're new here and this stuff is kind of seem excited to you and you want to talk about it more, again, there is a probabilistic modeling Discord server. If you go to the Patreon and you search Discord, it should show up on the first one, and there's a link here. Sometimes the link gets stale. Just let me know, and I'll put a new link up. Free to join server, and we talk about everything from philosophy to particular modeling problems, particular implementation computational problems. It's really meant to be a community for people who don't have a community otherwise. So feel free to join there. You can lurk. There's a ton of lurkers who are there all the time who don't never say anything. And a bunch of people more and more people who are having discussions. So feel free to come and lurk. Feel free to come and ask questions at any level. So long as you're focused on probabilistic modeling and in inference, you're good to go. So any question at any level on that topic is more than welcome. Otherwise, keep up on the Patreon for new writing comes out. Also have a newsletter. If you're interested in getting kind of updates once a month on anything new that might have come out. And you can subscribe to the Patreon for a bunch of bonuses and early content. Extra live streams you don't get access to unless you're a supporter at a certain level. But I do as much as I can freely, and we'll do another maybe Thanksgiving-ish Well, I have some teaching. We'll see how things fill out. But I try to do a winter office hours as well. So either we'll do a kind of a late fall or early winter office hours next. So if you have questions and you don't feel comfortable asking them on the Patreon or on social media or on the Discord server, especially, save them up. I'll throw another call, and you can ask your questions again there, and we'll hopefully have another good time. These were great questions. I had a lot of fun answering them, putting stuff together. I hope it was useful for most people. We've been going for a while. Thanks to everyone who's been tagging along. I'll give one last call for last questions while we're here, while I check to see if anyone is actually still watching. All right, I'll probably call it there. If you have questions that follow up, throw them on the Patreon or ask them on the Discord server. Otherwise, I'll hope to see you on any of those platforms I just mentioned, or in the worst case, on the next office hours. Thanks so much, everyone.